born from an overheated imagination. And yet, what if it's real? What if lurking in the darkness of space, in the bottomless depths of the universe, there exist objects so mysterious, so paradoxical, that they challenge the very nature of reality? Objects that turn our understanding of physics upside down. Objects that force us to rewrite textbooks and reconsider everything we thought we knew about the cosmos. They're called gravastars. Gravitational vacuum stars. Gravitational vacuum condensates. Ghosts of collapse. They have many names, but the essence is singular. They are potentially the most extreme, the most incredible, the most terrifying objects in the universe. And they might be real. Black holes. Forget about them. For a century we've frightened ourselves with black holes, these all-devouring monsters of spacetime, these cosmic vampires from which nothing can escape. We've trembled before them. Made movies about them. Written books. Created computer models of their accretion disks, their event horizons, their singularities. But what if all this time we've been afraid of the wrong thing? What if black holes are just a simplified version of reality? A convenient mathematical abstraction? An approximate solution to equations that works in theory but fails in the real cosmos? What if out there, in the actual universe we inhabit, something far stranger exists? Something that makes black holes look tame by comparison. Welcome to the world of gravastars, objects that may be even more terrifying, even more mysterious, even more incredible than anything we've ever imagined. This is a story about how science moves forward, stumbling in darkness. About how every truth turns out to be merely a stepping stone to an even stranger reality. About how the universe again and again proves itself more inventive than our wildest fantasies. Are you ready to gaze into an abyss that gazes back? Let us begin with what seemed like absolute truth. With what we accepted as fact. With black holes. Picture a star. Not an abstract point of light in the night sky, but a gigantic thermonuclear reactor the size of 1,000,000 Earths. A ball of plasma where every second millions of tons of hydrogen transform into helium, releasing energy capable of illuminating planetary systems trillions of kilometers around. This isn't just light. This is war. A battle of titans. A confrontation between two fundamental forces of nature. On one side, gravity. Merciless. Relentless. Forever pulling everything toward the center. It wants to compress the star into a point, to turn it into nothing, to crush every atom under unimaginable pressure. Gravity is a cosmic press, working without pause, without fatigue, without mercy. On the other side, thermonuclear pressure. The fury of fusion reactions. Photons and particles bursting outward with such force that they keep the star inflated, prevent it from collapsing. This is a shield against gravity. A defense against collapse. For billions of years these forces remain in balance. They dance a cosmic dance. They maintain a fragile balance between existence and annihilation. But nothing lasts forever. When the fuel runs out, when the thermonuclear furnace cools, when the last hydrogen atoms convert to heavier elements, the shield falls. The defense crumbles. And gravity wins. Collapse. This word doesn't convey even 1/100th of the horror of what occurs. A star that existed for billions of years implodes in mere seconds. Matter falls inward at velocities approaching light speed. The pressure becomes so monstrous that the electron shells of atoms shatter. Protons and electrons merge into neutrons. The very fabric of space begins to deform, distort, fold. And at the very end, when even neutron matter cannot resist gravity, when even the Pauli exclusion principle surrenders, she emerges. The black hole. More precisely, that's what we were taught. That's what textbooks said. That's what professors explained in universities around the world. A black hole is a place where gravity wins definitively. Where all the stars' mass collapses into an infinitely small point, a singularity. Where density becomes infinite and the laws of physics as we know them cease to function. Around this singularity forms an event horizon, a boundary of no return, a point of no return. To cross it means to vanish forever from the observable universe. Beautiful theory. Elegant mathematics. A solution to Einstein's equations found by Karl Schwarzschild back in 1916, when the First World War raged in Europe and Einstein himself had barely finished his general theory of relativity. For a century we believed this. For a century we built all of relativistic astrophysics on this foundation. But what if it's too simple? What if nature abhors infinities? What if the singularity is not reality but a mathematical artifact? What if there, where we see a black hole, something else exists? Physicists don't like infinities. They're dirt in the cleanliness of their mathematics. They're a warning signal indicating that the theory is breaking down somewhere, exceeding the limits of applicability. When infinities appear in your equations, it usually means one thing: you've missed something. You haven't accounted for some important effect. You've entered a domain where your theory no longer works. And black holes are full of infinities. Infinite density at the center. Infinite curvature of spacetime. Infinite redshift at the event horizon. These mathematical monsters lurk in the very heart of black hole theory, and physicists have never felt comfortable with them. Richard Feynman, one of the greatest physicists of the 20th century, once said, "If a theory gives infinity, then something's wrong with the theory." He understood. Nature is finite. The universe may be strange, paradoxical, counterintuitive, but not infinite at a specific point in space. And yet for decades we tolerated these infinities. We closed our eyes. We told ourselves, well, we don't have a better theory. We hid the singularity behind the event horizon, as if that solved the problem. We said, nothing can escape from inside, so we don't need to worry about what happens there. But this is self-deception. Physics must work everywhere. The laws of nature cannot simply turn off in certain places. The singularity is not a solution, it's an admission of defeat. It's a white flag thrown up in the face of ignorance. And some physicists understood this. They searched for alternatives. They tried to find ways to avoid the singularity. They believed there must exist something else, some structure, some mechanism that stops the collapse before it reaches infinite density. Wormholes. Planck stars. Boson stars. Fermion balls. Dozens of exotic objects were proposed over the decades. Each with its merits. Each with its problems. And then, in 2001, at the beginning of the new millennium, when the world was still recovering from the attacks of September 11th, two physicists published a paper that should have changed everything. Pauel Mazur and Emil Motola. Two names that few know outside a narrow circle of relativists. They proposed something radical. Something revolutionary. Something so strange that most of their colleagues simply didn't believe it. They called it a gravitational vacuum condensate. Or, more briefly, a gravistar. Scientific revolutions are rarely loud. They don't happen with an explosion, with fanfare, with headlines on the front pages of newspapers. More often they begin quietly, with a paper in a specialized journal that only a few dozen people will read. With an idea so strange that it's either ignored or ridiculed. The paper by Mazur and Mottola was exactly like that. Gravitational Condensate Stars and Black Holes, that was the title of their work. A dry, technical name concealing an idea capable of overturning astrophysics. What did they propose? Imagine a collapsing star. Gravity compresses it. Matter falls inward. Pressure builds. Temperature soars to billions of degrees. Everything is heading toward the formation of a black hole. But in the last moment, in the microsecond before the event horizon forms, something happens. Something fundamental. Something connected to the very nature of spacetime itself. The vacuum changes phase. Sounds absurd. Let's understand this. In quantum field theory, vacuum is not emptiness. It's not the absence of everything. Vacuum is the lowest energy state, filled with virtual particles, fluctuations, quantum effects. Vacuum is alive. It seethes with quantum activity, though we don't see it. And like any quantum field, vacuum can exist in different phases. Just as water can be ice, liquid, or vapor, three different phases of the same substance. Under normal conditions, vacuum is in one phase. But what happens under extreme conditions? Under the monstrous pressure of a collapsing star? Under the warping of spacetime close to critical? Mazur and Mottola hypothesized, vacuum can transition to another phase. A phase with negative pressure. A state that creates anti-gravity. Yes. Anti-gravity. Not repulsion in the usual sense, but something more subtle, more fundamental, an effect similar to dark energy, that same mysterious force accelerating the expansion of the universe. And this anti-gravity stops the collapse. Right at the threshold. Millimeters from where the event horizon should have formed. The star freezes in a state of almost collapse. Almost black hole. But not quite. This is a gravistar. Try to visualize this. Try to see with your mind's eye the structure of an object that defies intuition. On the outside, a thin shell. Incredibly dense. Matter compressed to such a degree that protons and neutrons practically touch. A hardness exceeding everything we know. A strength that cannot be measured in ordinary units. This shell has a thickness, possibly, of a Planck length, the smallest meaningful scale in physics, 10 to the minus 35 meters. Thinner than an atom by 10 to the 20th times. Thinner than a proton by billions of times. And yet this unimaginably thin shell holds everything together. It is the barrier between our reality and, what? Inside, vacuum. But not ordinary vacuum. Vacuum in an exotic state. Spacetime in a phase with negative pressure, with energy that pushes outward rather than pulling inward. It's like a bubble of anti-gravity, enclosed in the hardest shell in the universe. No singularity at the center. No point of infinite density. No place where physics stops working. There is only strange vacuum pressing from within, and matter compressed to the limit, holding that vacuum captive. Balance of forces. Balance again. But completely different from an ordinary star. In an ordinary star, thermonuclear pressure opposes gravity. Here, the quantum pressure of vacuum opposes the attempt of matter to collapse further. This is equilibrium on a knife's edge. Dynamic stability on the brink of impossibility. From the outside, a gravastar looks almost identical to a black hole. Almost. It possesses mass. It warps spacetime around itself just the same. It attracts matter, light, everything that comes too close. Its gravitational field is indistinguishable from that of a black hole of the same mass. But there is one critical difference: a gravastar has no event horizon. The boundary that appears to be a horizon is actually a solid surface. Incredibly close to where the horizon would be, but still not it. A photon's millimeters. Planck distances. But in physics, even such microscopic differences can have colossal consequences. Information doesn't disappear in a gravastar. It can reflect from the surface. Monstrously redshifted, yes. Stretched in time beyond recognition, yes. But not lost forever, as in a black hole. This solves one of the most agonizing paradoxes of modern physics. Stephen Hawking. A name that became synonymous with black holes. A physicist who devoted most of his life to studying these objects. And it was he who discovered the problem that tormented him until his death. In the 1970s, Hawking made an astounding discovery: black holes aren't completely black. They radiate. They evaporate. Slowly, incredibly slowly, but inevitably. Quantum effects near the event horizon birth pairs of virtual particles. One falls inside, the other flies away. To an external observer, this looks like radiation from the black hole. Hawking radiation. A triumph of theoretical physics. A connection between general relativity, quantum mechanics, and thermodynamics. But hidden in this discovery was a time bomb. If a black hole evaporates completely, and theory predicted that sooner or later this would happen, then what happens to the information about all the matter that fell inside? Information about every atom, every particle, every quantum state. According to quantum mechanics, information cannot simply disappear. This is a fundamental principle. The law of information conservation. To violate it means to destroy the entire edifice of quantum theory. But if a black hole evaporates through Hawking radiation, which is completely random and carries no information about what fell inside, where does the information go? The information paradox in black holes. A problem that split the physics community for decades. A battle of titans, relativists versus quantum physicists. Years of debates. Kilometers of written paper. Hundreds of articles and counter-articles. Hawking initially asserted that information really is lost. This shook the foundations of physics. Other physicists, especially Leonard Susskind and Gerard T. Hooft, fiercely disagreed. The black hole wars began, an intellectual battle lasting decades. Eventually, Hawking admitted his error. In 2004, he publicly agreed that information must be conserved. But exactly how it's conserved in a black hole? That remained a mystery. Gravastars offer an elegant solution. If there's no event horizon, if there's no true black hole, then there's no paradox. Information remains on the surface of the gravastar. Yes, monstrously distorted. Yes, stretched by time. But not lost. Problem solved. In principle, yes. In practice, everything is much more complicated. Because information stored on a surface of Planck density is fundamentally inaccessible. We cannot read it. We cannot decipher it. For all practical purposes, it's lost, even if it formally exists. It's like saying that information about a burned book is conserved in the atoms of smoke and ash. Technically true. Practically useless. But for physics, this matters. It's the difference between a theory that's consistent with fundamental principles and a theory that violates them. And gravastars are consistent. Black holes are not. Or at least their consistency requires additional, not fully understood mechanisms. Science is not a monolith. It's not a single army marching toward truth in orderly rows. Science is a battlefield of ideas, where every theory must fight for survival. Where skepticism is not a flaw but a necessity. Where every claim meets resistance. And the idea of gravastars met considerable resistance. Too exotic, said critics. Where's the proof? Where are the observations? Where are the experiments? Vacuum phase transition. Under what conditions? What physics describes this? What equations? A shell of Planck thickness? How can it be stable? Why doesn't it collapse? Why doesn't it rupture? Questions poured down like hail. And many of them were fair. Pauel Mazur and Emil Motola relied on semi-classical reasoning. They extrapolated known physics into a domain where, perhaps, a completely new theory is needed. They made assumptions about the behavior of vacuum under conditions we've never observed and possibly never can reproduce. Quantum gravity, the theory that should unite general relativity and quantum mechanics, still hasn't been constructed. We don't know exactly how spacetime behaves on Planck scales. We build guesses, models, hypotheses. But there's no solid knowledge. And gravastars are based on these shaky foundations. Moreover, many physicists pointed to stability problems. If such an object forms, will it be stable? Or will it instantly collapse into a true black hole? Or explode, torn apart by internal pressure? Numerical simulations gave contradictory results. Some showed that gravastars could be stable. Others, that they're unstable at the slightest perturbation. Still others demonstrated that everything depends on model details. On subtleties of the equation of state for matter in the shell. Debates continued. Continue to this day. But skepticism is not rejection. It's a demand for proof. And this is exactly what drives science forward. Over 2 decades since the initial paper, dozens of modifications of the gravastar idea appeared. Physicists are inventive folk. They took the basic concept and began experimenting with it, changing parameters, exploring alternative scenarios. Gravastars with anisotropic shells, where pressure differs in radial and tangential directions. This makes the construction more stable but adds complexity to the mathematics. Gravastars with multiple shells, an onion-like structure where layers of normal matter and exotic vacuum alternate. A matryoshka of phase transitions. Charged gravastars, objects with electric charge, adding electromagnetic effects to gravitational ones. This makes them even stranger but perhaps more realistic. Rotating gravastars, after all, real stars rotate, and post-collapse objects should rotate too. Angular momentum adds additional complexity, additional forces, additional ways to stabilize or destabilize. Each modification was investigated. Each analyzed mathematically. Each checked with numerical simulations. And gradually, slowly, the picture became clearer. Gravastars possibly can exist. Possibly are stable. Possibly form in the real universe. But possibly is not the same as definitely. Proof was needed. Observations were needed. Signs that would distinguish a gravastar from a black hole were needed. And here begins the most intriguing part. How do you distinguish a gravastar from a black hole? It's a question that sounds simple, but the answer is devilishly complex. Both objects are massive. Both are compact. Both warp spacetime almost identically. Both capture light, matter, everything that comes too close. To an astronomer observing from afar, they look practically the same. But practically is the key word. There are subtle differences. Barely perceptible. Requiring our most sensitive instruments and most sophisticated analysis techniques. But they exist. The first difference, gravitational wave echoes. When two black holes merge, they create ripples in the fabric of spacetime. Gravitational waves race through space at light speed. We've learned to detect them, LIGO and Virgo, giant interferometers capable of registering space stretching smaller than the width of a proton. Black hole mergers produce a characteristic signal, a chirp, rising frequency, then sharp decay as the new, merged black hole settles down. This signal is predicted in detail by general relativity. We know what it should look like. But if one or both merging entities are gravastars, then there should be echoes. Reflections from the solid surface instead of disappearance behind the horizon. Additional oscillations, additional components in the signal. Physicists have searched for these echoes. They've combed through detector data. Applied sophisticated processing algorithms. Some claim to have found hints of these echoes. Others said these were statistical fluctuations, noise, processing artifacts. Debates continue. Data is inconclusive. We're at the edge of our instrument sensitivity. The second difference, quasi-periodic oscillations in X-ray emission. When matter falls onto a compact object, it forms an accretion disk, a spiral of superheated gas that gradually loses energy and angular momentum, approaching the central body. This disk radiates in the X-ray range. And in this radiation, oscillations can be detected, periodic changes in brightness. They arise from the motion of matter in strongly curved spacetime near the compact object. The frequencies of these oscillations depend on details of the gravitational field. And if the object at the center is a gravastar with a solid surface instead of an event horizon, the frequencies should differ. Slightly. But measurably, if our telescopes are accurate enough. Again, observations at the edge of possibility. Again, debates about the significance of results. The third difference, gravitational waves from oscillating objects themselves. If a gravastar is perturbed, say, it swallowed a small portion of matter or was subjected to a gravitational shock from a passing star, it should ring like a bell. Oscillate. But the character of these oscillations differs from those of a black hole. A black hole has characteristic ringing frequencies, quasi-normal modes. They depend only on mass and spin. Mathematically, this is beautifully described by the perturbed Kerr metric. A gravastar's frequencies are different. They depend on the shell structure, on the equation of state of matter, on details of the internal vacuum state. The spectrum is richer, more complex. Detecting these oscillations means distinguishing the objects. But this requires incredibly precise measurements. And, critically, a nearby event. Gravitational waves from an oscillating gravastar are weaker than from a merger and harder to detect. The fourth difference, shadows in Event Horizon Telescope images. In 2019, humanity first saw the shadow of a black hole. More precisely, an image of M87-, the supermassive black hole at the center of galaxy M87. A dark region in the center, surrounded by a glowing ring of the accretion disk. This was a triumph. An image consistent with general relativity predictions. Confirmation of event horizon existence. Or was it? If the object at the center is a gravastar, its shadow should look just slightly different. The size of the dark area slightly differs. The shape may be somewhat deformed. Details of brightness at the boundary have a different character. These differences are so small that even EHT's capabilities may be insufficient for unambiguous distinction. Even more sophisticated instruments are needed. Longer interferometry baselines. More telescopes in the array. More sensitive receivers. But one day, perhaps soon, we may be able to say for certain. Are there real gravastar candidates? The billion-dollar question. Or rather, the billion-light-year question. Every time a compact object merger is detected, every time a new black hole candidate system is discovered, groups of physicists begin analyzing, could this be a gravastar? GW190521, a merger of two massive objects creating a gravitational wave detected in 2019. The component masses fell into the forbidden zone, a range where black holes shouldn't form according to standard stellar evolution scenarios. This anomaly required explanation. Could these have been gravastars? Some physicists argued, yes. Gravastars can form with masses unattainable for ordinary black holes of stellar origin. Exotic physics creates exotic objects. Others remain skeptical. Alternative explanations, intermediate black holes formed through non-standard mechanisms, mergers in dense star clusters, dynamical interactions, could also explain observations. GW170817, a neutron star merger, the first event where gravitational waves were accompanied by electromagnetic radiation. A kilonova flash, gamma-ray burst, afterglow across all ranges. A treasure trove of data for astrophysicists. Analysis showed the merger product was a massive compact object. Possibly a black hole. Possibly a hypermassive neutron star. Possibly a gravastar. Again debates. Again uncertainty. And so with each new event. Data permit interpretation. But don't demand it. Gravastars remain a possibility, not a necessity. The problem is that the differences are too subtle. Our instruments, for all their incredible sensitivity, operate at the limit. We see objects from billions of light-years away, through distorted spacetime, through interference from dozens of noise sources. Extracting the tiny signal indicating a gravastar from this cacophony is a task of colossal complexity. But we don't give up. Suppose for a moment that gravastars are real. That they exist in the universe, hiding under the mask of black holes. What happens then? What makes them more terrifying than black holes? This isn't a question of literal danger. Neither a gravistar nor a black hole poses a threat to Earth. The nearest black hole is thousands of light years from here, and a gravistar at that distance wouldn't harm us either. No. The terror here is intellectual. Philosophical. It's the terror before a reality even stranger than we thought. Before a universe that again proves more inventive than our imagination. Let's start with the surface. A black hole has no surface. The event horizon is not a material boundary, it's simply a place in spacetime from which there's no return. Crossing it doesn't mean hitting something. It means entering a region from which your trajectory inevitably leads to the singularity. For a freely falling observer, crossing the horizon might not be remarkable at all, only later would they realize they cannot return. A gravistar has a surface. Solid. Material. You can collide with it. And that collision would be specific. Imagine you're falling toward a gravistar. Accelerating under monstrous gravity. Speed increasing. Approaching light speed. Spacetime around you increasingly distorting. Time slowing relative to a distant observer. And then, impact. But what kind of impact? With what density of matter do you collide? Matter in a gravistar's shell is compressed to Planck density, about 10 to the 96th kilograms per cubic meter. That's 10 to the 80th times denser than an atomic nucleus. This is density at which quantum gravity becomes the dominant force. Colliding with such a surface means colliding with matter so dense that the concept of collision loses meaning. You won't simply be torn apart. You'll be torn into atoms. Atoms torn into particles. Particles decomposed into quantum foam. The impact energy at relativistic velocities would transform you into a flash of radiation, so bright and hot that to an external observer it would look like a micro-explosion on the object's surface. A black hole is more merciful. There you're simply consumed. Information about you disappears behind the horizon, or is preserved in some mysterious way, but in any case you're gone. A gravistar though, a gravistar would smear you across its surface in a two-dimensional holographic pattern of quantum information. This isn't just death. This is quantum annihilation. But there's something even more frightening. What happens if a gravistar destabilizes? Imagine, the balance of forces is disrupted. Maybe the object swallowed too much matter. Maybe it merged with another compact object. Maybe simply enough time passed for quantum fluctuations to disturb the fragile equilibrium. The shell begins to fail. Inside, vacuum with negative pressure. Anti-gravity, restrained by the shell. What happens when containment weakens? One scenario, collapse. The shell can't hold, implodes inward, and the gravistar transforms into a true black hole. A singularity forms, the event horizon finally establishes itself. The object transitions from one exotic state to another. To an external observer, this might look like a sudden change in gravitational properties. Quasi-normal modes change. Echoes disappear. The object becomes more black. Another scenario, explosion. Internal pressure ruptures the shell. Exotic vacuum bursts outward. And then something occurs for which we have no good analogies. This isn't a supernova, there a star explodes, matter flies apart, energy from thermonuclear fusion and gravitational collapse is released. This isn't a gamma-ray burst, though there will be radiation, very intense radiation. This is an explosion of the fabric of spacetime itself. A release of vacuum energy locked in an exotic state. A quantum phase transition in reverse, occurring catastrophically fast. The energy. The object's mass multiplied by the speed of light squared. E equals mc squared. All of it, or a significant portion of it, released in milliseconds. For an object of several solar masses, this means energy equivalent to 100 of the most powerful supernovae occurring simultaneously. A gamma-ray flash capable of sterilizing planets within hundreds of light-years. A gravitational shock capable of disturbing a galaxy's structure. This is purely hypothetical, of course. We don't know if gravastars can explode. We don't know if they're stable long-term. We don't even know for certain if they exist. But if they do, if they can explode, then the universe harbors time bombs, each capable of releasing energy exceeding anything we've observed in space except the Big Bang itself. Sleep well. Let's return to the information problem. To Hawking's paradox. In a black hole, information, about every atom that fell inside, about every quantum state, is presumably conserved. But how? Where? In what form? String theory offers the holographic principle: all information is encoded on the event horizon, in a two-dimensional structure invisible to an external observer. This is mathematically elegant but physically enigmatic. In a gravastar, everything is simpler and more complex simultaneously. Information remains on the surface. Literally. Every particle falling onto a gravastar interacts with the incredibly dense matter of the shell. The quantum state of the falling matter imprints itself on the quantum state of the surface. This isn't a metaphor. This is a physical process. Quantum entanglement between falling matter and shell matter. Information about what fell is distributed across the entire surface, mixing with already existing information. As the gravastar evaporates through Hawking radiation, yes, gravastars evaporate too, though the process differs from black holes, information gradually releases back. Incredibly slowly. Incredibly entangled. But not lost. Paradox solved. In principle, yes. In practice, everything is much more complicated. Because information stored on a surface of Planck density is fundamentally inaccessible. We cannot read it. We cannot decode it. For all practical purposes, it's lost, even if it formally exists. It's like saying information about a burned book is conserved in smoke and ash atoms. Technically true. Practically useless. But for physics, this matters. It's the difference between a theory consistent with fundamental principles and one that violates them. And gravastars are consistent. Black holes aren't. Or at least their consistency requires additional, not fully understood mechanisms. If gravastars exist, how many are there? This is a question impossible to answer without observations. But we can speculate. Every massive star collapsing at life's end potentially could form a gravastar instead of a black hole. Conditions must be suitable: sufficient mass, correct metallicity, certain rotation rate. But if conditions are met, gravastar. How many massive stars have collapsed since the first stars formed in the universe? Billions. Trillions. In our galaxy alone, hundreds of millions. If even 1% of them formed gravastars, we're talking millions of these objects just in the Milky Way. In the observable universe, quintillions. An army of gravastars masquerading as black holes. Each, a bomb of quantum vacuum. Each, an information repository. Each, a mystery awaiting solution. And that's only stellar masses. What about supermassive objects in galaxy centers? Sagittarius A star, the object at our galaxy's center, with a mass of 4 million suns. We think it's a black hole. But what if it's a gravastar? Differences would be even subtler at such scales. Even harder to verify. But the consequences are colossal. A supermassive gravastar would have different structure, different formation history, different influence on the surrounding galaxy. Understanding that galaxy centers contain gravastars, not black holes, would rewrite galactic evolution theory. And if they explode, a supermassive gravastar explosion would destroy the galaxy completely. Scatter stars across intergalactic space like a dandelion blown by wind. Do we observe such events? Are there galaxies that suddenly, catastrophically disintegrated? Honestly, we don't know what to look for. We don't know what a galaxy's death from central gravastar explosion looks like. We're not even sure it's possible. But if it is, the universe is even more terrifying than we thought. To definitively resolve the question of gravastar existence, we need better tools. More sensitive detectors. Capable of registering the subtlest differences in gravitational waves. LIGO and Virgo are engineering triumphs. But they operate at high frequencies. Detecting stellar mass mergers. They're blind to low-frequency signals, to events involving supermassive objects. This is where LISA enters the stage. Laser Interferometer Space Antenna. A space-based gravitational wave detector, launch planned for the 2030s. 3 satellites forming a triangle with sides of 2.5 million kilometers. Flying in formation, maintaining position with nanometer precision. Exchanging laser beams, tracking the tiniest changes in distances between them. LISA will be sensitive to low frequencies. To massive black hole, or gravastar, mergers. To events in galaxy centers. To processes inaccessible to ground-based detectors. And LISA may provide the definitive answer. Because differences between gravastars and black holes are more pronounced in the low-frequency range. Echoes more noticeable. Quasi-normal modes more separated. Statistical significance higher. If gravastars exist, LISA will find them. Or at least find signs that cannot be ignored. This isn't just a question of curiosity. It's a question of understanding gravity's nature, spacetime's nature, reality's very nature. The Event Horizon Telescope showed we can image shadows of compact objects. But EHT resolution is limited. Baseline size, Earth's diameter. We can't make it larger unless we build telescopes in space. And that's exactly what's being planned. Projects for space interferometers operating in millimeter and submillimeter ranges. Satellites in Earth orbit or even solar orbit, creating baselines millions of kilometers long. With such resolution, we could see not just the shadow but structural details near the horizon, or its absence. We could distinguish a gravastar's solid surface from a black hole's event horizon. We could see photon orbits, light trajectories captured in stable or quasi-stable orbits around the object. Their structure depends on whether there's a horizon or solid surface. We could observe accretion with unprecedented resolution. See how matter falls onto the object, how it interacts with the surface, or disappears behind the horizon. Process dynamics differ, and with sufficient resolution these differences become visible. Technologies exist. Physics is understood. Only time, money, and will are needed. And, of course, a bit of luck. Because even the best instruments are useless if nature doesn't provide suitable objects for study. Can we recreate gravistar conditions on Earth? Even in principle? Answer, no. Absolutely not. Not even close. Pressures necessary for vacuum phase transition, if such a transition is even possible, lie beyond anything we can create. Particle accelerators, even the most powerful, even future colliders, reach energies far from the Planck scale. The difference, about 15 orders of magnitude. It's like comparing an atom's size to the solar system's size. We cannot create a gravistar. We cannot even approach its formation conditions. But we can build models. Computer simulations. Numerical solutions to Einstein's equations with various assumptions about matter and vacuum behavior. And we do this. Hundreds of physicists worldwide work on gravistar models. Explore different scenarios. Predict observational signatures. Prepare the ground for experimental verification. Because ultimately science is a dialogue between theory and observation. Theory proposes ideas. Observation tests them. And in this dance, this interaction, knowledge is born. We approach questions that go beyond physics. Questions about reality's nature, about the limits of knowledge, about what it means to exist. Gravistars, if they're real, exist at the very boundary of the knowable. They exist in conditions so extreme that our usual concepts begin to break down. What is a surface when speaking of a shell of Planck thickness? Does it even make sense to speak of inside and outside when quantum effects dominate? We use words from everyday experience to describe phenomena without analogues in daily life. We build models based on equations that perhaps aren't applicable in these conditions. This isn't science's flaw. It's its honesty. Science says, we don't know, but we're trying to find out. It doesn't claim final answers. It offers best approximations based on available data. And this is its strength. The ability to admit uncertainty. The ability to say, perhaps we were wrong. Here's a new idea. Let's test it. Gravistars are a proposal. A hypothesis. A possibility to investigate. They may prove real. May prove fantasy. Or truth may lie somewhere in between, objects resembling gravistars but not quite as initial models predicted. We'll learn with time. With observations. With data. The history of science is a history of surprises. We thought Earth was flat. Turns out, round. We thought Earth was the center of everything. Turns out, an ordinary planet around an ordinary star. We thought the universe was static and eternal. Turns out, expanding and has a beginning. We thought atoms were indivisible. Turns out, composed of particles. Which are composed of quarks. Which perhaps are composed of strings. Each time we thought we'd reached bottom, understood the basics, the universe said, not so fast. There's another level. Gravastars are another turn in this endless story. Another reminder that reality is richer than our theories. Maybe black holes are a simplification. A convenient model working in first approximation but missing important details. Maybe real objects are more complex, more exotic, stranger. Or maybe gravastars are a dead end. A beautiful idea unrelated to reality. A mathematical artifact not realized in nature. We don't know. Not yet. But the very fact that we can ask these questions, that we can build models, make predictions, plan observations, this is a miracle. A miracle of human mind, capable of gazing into cosmic abysses and trying to understand what hides there. Why do we call gravastars terrifying? Why deadlier than black holes? Not because of physical danger. No. The terror here is intellectual. Existential. The terror of realizing that the universe isn't obligated to be comprehensible. That it may contain objects and phenomena so strange they challenge our ability to grasp them. Black holes we've mastered. Over a century they transformed from mathematical abstraction into real objects we observe, study, even photograph. They became part of our cosmological worldview. We know how they form, how they evolve, how they influence surroundings. Gravastars though, this is a step into the unknown. They require physics we don't yet fully understand. Quantum gravity. Vacuum phase transitions. Phenomena at Planck scales. They remind us of our knowledge's boundaries. That behind every answer hide a dozen new questions. That the universe is deeper than we can imagine. And there's something eerie in this. Vertiginous. Whenever we think we're close to understanding reality's fundamental nature, something appears that throws us back. Or rather, pushes us forward, toward even greater mysteries. This is scientific progress. Movement from island of ignorance to island of ignorance, with an ocean of unknown between and around them. Gravastars are a reminder that the ocean is vast. That we've only begun to explore it. Gravastars aren't the only alternative to black holes. Physicists are inventive, and over decades many exotic objects were proposed, each with distinctive features. Boson stars, hypothetical objects composed of bosons held together by gravity and quantum effects. Unlike ordinary stars where thermonuclear pressure matters, here stability is provided by Heisenberg's uncertainty principle. Bosons can occupy the same quantum state, allowing creation of very dense but non-collapsing objects. Sounds esoteric? Certainly. But the mathematics works. Equations have solutions. The question is only whether suitable bosons exist in nature and in sufficient quantity. Dark matter? Possibly. If dark matter particles are bosons with right properties, they could form stars. Invisible in ordinary light but detectable by gravitational effects. Fermion balls, analogous concept but for fermions. Pauli exclusion principle prevents fermions from occupying the same quantum state, creating pressure that can resist gravity. Neutron stars are examples of fermion balls, but there are suggestions of even more exotic variants. Quark stars, objects where matter is decomposed to quarks. Neutrons destroyed, quarks free, but not yet collapsed into a black hole. Strange matter predicted by quantum chromodynamics. Possibly stable at sufficient density. Preon stars, hypothetical objects if quarks themselves consist of more fundamental particles, preons. Pure speculation at the moment, but physics doesn't exclude such possibility. Planck stars, objects where quantum gravity effects stop collapse at Planck scales. In some sense similar to gravastars, but the stabilization mechanism differs. Here the discreteness of spacetime at Planck scales matters. Wormholes, tunnels in spacetime connecting distant regions of the universe or even different universes. Mathematically permissible solutions to Einstein's equations, requiring however exotic matter with negative energy density. Stability questionable. Formation, a mystery. Each of these objects solves some problem. Avoids singularity. Conserves information. Provides an alternative to black holes. And each faces its own problems. Uncertainty in physics. Doubts about stability. Absence of observational confirmation. Gravastars are one candidate in this zoo. Perhaps the most plausible. Perhaps not. Time will tell. What if truth isn't that only one of these objects is real? What if nature uses all these possibilities? What if depending on conditions, mass, rotation, composition, formation history, a collapsing star can transform into different types of compact objects? Small mass, neutron star. Medium mass, quark star or gravastar. Large mass, black hole. Or vice versa. Or in any combinations. The universe isn't obligated to be simple. It can be diverse. Can use the full spectrum of possibilities provided by physics. And then the observer's task isn't simply determining what's correct, but mapping all realized variants. Understanding under what conditions each object type forms. This changes perspective. Instead of binary choice, black hole or gravastar, we get a continuum of possibilities. A landscape of compact objects, each with its niche in parameter space. Some simulations hint at such possibility. Show that under certain initial conditions an object resembling a gravastar forms, and under others, a classical black hole. The boundary between them may be thin. A small mass change, a slight difference in angular momentum, and collapse result changes. Nature experiments. We observe results. And try to understand patterns. Does all this sound like pure abstraction? Like physicists' games unrelated to real life? In some sense, yes. Gravastars, if they exist, are so far away they present no immediate practical importance to humanity. They won't change our daily lives. Won't help solve climate change or hunger or war problems. But fundamental science has a way of bearing unexpected fruit. General relativity was pure abstraction when Einstein formulated it. Who could have thought that a century later it would be critical for GPS operation? Quantum mechanics seemed an esoteric mind game in the 1920s. Today half the world economy is based on quantum effects, semiconductors, lasers, MRI scanners. Understanding extreme states of matter and spacetime may lead to technologies we cannot even imagine now. Vacuum manipulation. Control over quantum phase transitions. New energy sources based on exotic matter states. This is speculation, of course. But history teaches, understanding nature's fundamental principles sooner or later finds application. More immediate impact, on our worldview. How do we see our place in the universe? How well do we understand reality? If gravastars are real, this means the universe is even more quantum than we thought. That quantum effects are important not only at microscopic scales but at cosmological ones. That vacuum is not emptiness but an active participant in cosmic dynamics. This reinforces the view of the universe as a quantum system. Not as classical spacetime where quantum effects are small corrections, but as fundamentally quantum reality where classical physics is merely an approximation. This also reminds us of human knowledge's boundaries. We're beings evolved for navigating a world of middle scales, sizes and energies far from Planckian. Our intuition is tuned to this world. When we go beyond its limits, into the very small, quanta, or very large and dense, relativistic, intuition fails. Gravastars show how far we can go using mathematics and logic, even when intuition is silent. They're a triumph of abstract thinking. The human mind's ability to construct models of reality it has never seen and may never see directly. And simultaneously, a reminder of humility. That our models are always approximations. That reality may be even stranger than our boldest theories. There's another reason gravastars matter. They inspire. Each generation needs its big questions. Mysteries that push knowledge boundaries. Challenges requiring the best minds and most sophisticated instruments. For previous generations these were atomic energy, space exploration, genome decoding. Projects that mobilized resources and talents, created new technologies and new science branches. For our generation and the next, the nature of compact objects, quantum gravity, spacetime's fundamental structure. Gravastars are a concrete goal. A testable hypothesis. Predictions comparable with observations. This attracts minds. Motivates students to become physicists. Inspires engineers to build better detectors. And in the process of pursuing these goals, even if gravastars prove fantasy, we advance science. Develop new methods. Discover the unexpected. Because that's how exploration route to India and found America. We seek gravastars. What will we find? Time will tell. Gravastars don't exist in a vacuum, ironic, considering they're filled with special vacuum. They're part of a broader cosmological picture. And the two biggest mysteries of modern cosmology, dark matter and dark energy, may relate to gravastar physics. Dark energy, the mysterious force accelerating universe expansion. We know it exists because we observe its effects, distant galaxies flying apart ever faster. But what is it? Where does it come from? The simplest explanation, cosmological constant, energy of vacuum itself. Vacuum has non-zero energy density creating repulsive gravitational effect. Sound familiar? This is exactly what happens inside a gravastar. Vacuum in an exotic state with negative pressure. Is it possible that the mechanism stabilizing gravastars is connected to the mechanism determining dark energy? That vacuum phase transitions occurring in extreme conditions of compact objects give us a key to understanding vacuum behavior in the universe as a whole? Some physicists explore this possibility. Build models where gravastar vacuum energy and cosmological constant are manifestations of the same physics. If so, studying gravastars isn't just a question of understanding compact objects. It's a window into spacetime's fundamental nature, into mechanisms governing the entire universe's evolution. Dark matter, another mystery. 85% of universe matter is invisible. We know of its existence by gravitational effects. Galaxies rotate faster than they should if containing only visible matter. Galaxy clusters are held together by greater gravity than visible matter creates. But what is dark matter? Particles. What kind? We build detectors, search for direct collisions of dark matter particles with ordinary matter. So far unsuccessfully. Alternative idea: what if part of dark matter isn't particles but compact objects? Objects that don't emit light or emit it so little we cannot detect them. Stellar mass black holes. Boson stars. Gravastars. If gravastars formed from primordial density fluctuations in the early universe, before star formation, they could comprise a significant dark matter fraction. A population of primordial gravastars scattered through galaxies, creating gravitational effects but practically invisible. This is speculative. Calculations show compact objects can explain only a small dark matter fraction. But even a small fraction matters. Every percent we can explain brings us closer to solving the mystery. The Big Bang. 13.8 billion years ago. The universe was incredibly hot, incredibly dense. Matter and energy in states we can barely imagine. In the first fractions of a second after the Big Bang, in the Planck epoch, the first 10 to the minus 43 seconds, physics as we know it doesn't apply. Quantum gravity effects dominate. Spacetime fluctuates. Vacuum undergoes phase transitions. The very phase transitions that perhaps occur when gravastars form. Studying gravastars, we're perhaps studying early universe relics. Mechanisms active in cosmos's first moments, preserved in these extreme objects. It's like archaeology, but not of Earth, but of time itself. Gravastars are fossils from the Planck epoch. Samples of physics operating when the universe was younger than 1 second. If we can understand gravastars, we may understand what happened in those first moments. How the universe evolved from quantum foam to classical spacetime. What phase transitions vacuum underwent. How matter separated from antimatter. Grand questions. Questions about the origin of everything. And gravastars are one path to answers. Let's briefly immerse in mathematics. Don't worry, we won't use formulas, promise to avoid complex terms. But understanding how physicists investigate gravastars requires at least general understanding of methods. At the foundation of everything, Einstein's equations. 10 interrelated partial differential equations connecting spacetime curvature with matter and energy distribution. Beautiful. Elegant. And extremely complex. For most situations, Einstein's equations have no analytical solutions. We cannot simply solve them like a school quadratic equation. Instead, we build approximations, use numerical methods, simulations on supercomputers. For gravastars, the task is particularly complex. We must describe matter in extreme states, densities approaching Planckian. We must include quantum effects in classical gravity equations. We must model vacuum phase transitions whose physics we understand only partially. This requires assumptions. Simplifications. Model equations of state, relationships between pressure and matter density. Different assumptions give different results. Some models show stable gravastars. Others, unstable configurations collapsing in microseconds. Which model is correct? We don't know. We have no experimental data for such densities and pressures. We extrapolate known physics far beyond its tested applicability. It's like building a skyscraper on shaky foundation. The structure may prove strong, may collapse. Everything depends on details we cannot verify directly. And yet we try. Because this is the only way forward. Build models, make predictions, compare with observations, correct models. Iterative process. Gradual approach to truth. Unable to observe gravastar formation directly or recreate conditions in laboratory, physicists turn to computer simulations. Modern supercomputers are capable of astonishing things. They model galaxy collisions, star evolution, black hole mergers. Each simulation, a virtual experiment where we can control parameters, change conditions, observe results. For gravastars, simulations are especially important. We can set initial conditions, a collapsing star of certain mass and composition. Include various matter equations of state. Add effects of rotation, magnetic fields. Then run the simulation and see what happens. Does a stable gravastar form? Or does it collapse into a black hole? Or explode? What gravitational waves are generated? What electromagnetic signals? Each simulation answers these questions for a specific parameter set. Running thousands of simulations with different parameters, we can map possibilities. Determine under what conditions gravastars are stable and under what they aren't. The problem is simulations are limited by available computational resources. Modeling Planck scales in a kilometer-sized object is an inconceivable task. The scale difference is too great. Therefore simplifications are used. We model the shell as a continuum, ignoring quantum structure at small scales. We use averaged equations of state, not accounting for quantum fluctuation details. Results are informative but not definitive. They show what's possible within our models. But reality may differ. Nevertheless, each simulation is a step forward. Each result, a puzzle fragment. Gradually the picture becomes clearer. Besides numerical simulations, physicists use analytical methods, attempts to find exact or approximate equation solutions. For gravastars with high symmetry, for example, perfectly spherical, non-rotating, analytical solutions can be obtained. They're elegant, give deep understanding of object structure. The Mazur-Motola solution was the first example of such analytical approach. They found a configuration satisfying Einstein's equations, representing a stable object without event horizon. Since then many physicists have developed this work. Added rotation, solutions for rotating gravastars. Included electric charge. Considered multiple shells. Each extension complicates mathematics but enriches understanding. Analytical methods are also used to investigate stability. We can take a gravastar solution and study how it reacts to small perturbations. Is it stable? Or do perturbations grow, destroying structure? This is linear stability analysis, a standard physics tool. It doesn't give the full picture, nonlinear effects may be important, but provides first approximation. Results are mixed. Some gravastar configurations are stable to small perturbations. Others aren't. The stability boundary depends on model details. This is typical for physical systems on the edge of existence. Small parameter changes can shift the system from stability to instability. Nature loves balancing on the edge. Ideas from cutting-edge physics often seep into mass culture. Black holes became movie stars, novel subjects, TV show features. They entered collective consciousness as symbols of the unknown, unknowable, terrifying. Gravastars haven't yet achieved such status. But this may change. Imagine a film or novel where protagonists encounter a gravastar. An object looking like a black hole but not being one. Where a solid surface could, in principle, serve as a landing site, though gravitational tidal forces would tear any ship apart long before reaching the surface. Where inside hides exotic vacuum, whose energy if released could power a civilization or destroy it. Where quantum physics becomes macroscopic and reality's laws distort beyond recognition. Science fiction loves such concepts. They provide rich ground for speculation, for exploring what if. What if a civilization learned to create gravastars artificially? Use them as energy sources, controlling vacuum phase transitions. Or as weapons, threatening to release contents and destroy star systems. What if inside a gravastar spacetime is so distorted that time flows differently? That what seems like seconds inside are millennia outside? Or vice versa? What if gravastars are gateways to other universes, if the exotic vacuum inside connects to different spacetime regions? These are speculations. Fantasy. But science fiction has always been inspired by real science's edge. And gravastars stand right at that edge. Perhaps one day they'll be as iconic as black holes. Perhaps children will grow up learning about them in school. Perhaps humanity's far future will involve interacting with these objects, harvesting their energy, avoiding their dangers. Or perhaps they'll remain a footnote in physics history. An interesting idea that didn't pan out. A path not taken. But for now, they're a possibility. A mystery. A challenge. And mysteries are what drive us forward. They're what make us human. The desire to understand, to explore, to push beyond the known. Gravastars embody this desire. They represent our refusal to accept easy answers. Our insistence that reality may be stranger, richer, more wonderful than we imagine. They remind us that the universe doesn't reveal its secrets easily. That every answer we find opens new questions. That the more we learn, the more we realize how much we don't know. And yet we persist. We build detectors. We run simulations. We make observations. We test hypotheses. Because this is what science is. Not a collection of facts but a process. A way of asking questions about nature and listening carefully to the answers. Gravastars may exist. They may not. The universe will tell us, if we ask the right questions in the right way. And regardless of the answer, the journey will have been worthwhile. Because in seeking gravastars, we'll learn about quantum gravity, about spacetime's nature, about matter's behavior at extremes. We'll push technology forward. We'll inspire the next generation. We'll expand human knowledge's boundaries. This is the promise of fundamental science. Not immediate practical application but deep understanding. Understanding that eventually, unpredictably, leads to technologies and insights we cannot foresee. Einstein developing general relativity had no thought of GPS. Quantum mechanics pioneers never imagined computers. The scientists proposing gravastars don't know what their ideas might lead to. But that's the beauty of it. Science isn't about knowing the destination. It's about the journey into unknown territory. And gravastars, whether real or imaginary, are taking us on quite a journey. Through the mathematics of curved spacetime. Through the quantum physics of vacuum states. Through the observational astronomy of gravitational waves and X-ray emissions. Through the philosophy of what it means for something to exist. This journey challenges us. It stretches our minds. It forces us to question assumptions we didn't know we were making. What is space? What is time? What is matter? What is vacuum? These seem like simple questions. Children ask them. But the more deeply we probe, the more we realize how little we understand. Space isn't an empty stage where events unfold. It's dynamic, responsive, participant in cosmic drama. It can curve, twist, ripple with waves. Time isn't universal clock ticking uniformly everywhere. It's flexible, relative, different for different observers in different gravitational fields. Matter isn't solid stuff. It's concentrated energy, quantum probability waves, fields permeating space. Vacuum isn't nothing. It's seething quantum activity, virtual particles, potential energy waiting to manifest. And gravastars, if they exist, combine all these strange truths into one object. They're where space curves maximally without breaking. Where time slows to near standstill at the surface. Where matter reaches maximum density. Where vacuum transitions to exotic state. They're nature's extreme experiment. A test of physics at its limits. And we're privileged to live in a time when we can actually investigate them. When our technology has advanced enough to detect gravitational waves, to image compact objects, to run simulations of extreme physics. A century ago, this would have been impossible. A century hence, it may be routine. We stand at a unique moment in history. When gravastars transition from wild speculation to testable hypothesis. When we can actually gather data that might confirm or refute their existence. This moment won't last forever. Soon we'll know. LISA will fly. Better telescopes will observe. More mergers will be detected. And then we'll have our answer. If gravastars exist, physics changes. Textbooks rewrite. New research avenues open. Technology eventually follows. If they don't exist, that's also valuable knowledge. It constrains theories. It tells us something about how nature works, that certain configurations, while mathematically possible, aren't realized in reality. Either way, we win. Because we'll know more than we do now. And knowledge, understanding, insight, these are humanity's greatest treasures. More valuable than gold, more lasting than monuments. Civilizations rise and fall. Technologies become obsolete. But understanding nature's fundamental workings is eternal. Einstein's insights about spacetime will be true 1,000,000 years from now. Newton's laws of motion will still apply. The quantum principles we've discovered won't change. And if we discover that gravastars exist, or definitively prove they don't, that knowledge will last forever. This is what motivates physicists. Not fame or fortune, physics rarely provides either. But the chance to add to humanity's permanent knowledge base. To solve a mystery that has puzzled us. To understand something about the universe that no one has understood before. It's a noble calling. A worthy pursuit. And gravastars, deadly or not, terrifying or not, are a magnificent mystery to pursue. They challenge everything we thought we knew about collapsed stars. They require us to think deeply about quantum gravity. They push us to build better instruments. They inspire new generations of scientists. Whether they prove real or imaginary, they've already served a purpose. They've sparked debates, inspired research, driven technological development. And they've reminded us of something crucial: the universe is under no obligation to make sense to us. It is what it is, regardless of our theories or preferences. Our job is to observe carefully, reason clearly, and follow the evidence wherever it leads. Even if it leads to objects stranger than black holes. Objects that seem impossible but might just be real. Objects that embody the terrifying beauty of physics at its most extreme. Gravastars. Dead stars that aren't quite dead. Black holes that aren't quite black. Singularities that aren't quite singular. They occupy the liminal space between existence and non-existence. Between known physics and the unknown. Between what we can imagine and what actually is. And perhaps that's fitting. Because the frontiers of knowledge are always liminal spaces. Places where old certainties fade and new possibilities emerge. Where we grope in darkness, not quite sure what we'll find. This is uncomfortable. Humans crave certainty. We want definite answers, clear categories, firm ground beneath our feet. But the universe doesn't care about our comfort. It is what it is. And if that includes gravastars, objects that violate our intuitions, that challenge our theories, that force us to expand our understanding, then so be it. We'll adapt. We always do. We'll build new models. We'll revise our theories. We'll expand our conceptual frameworks to accommodate new realities. This is how science progresses. Not smoothly, not easily, but inexorably. Each generation building on the previous one. Each discovery opening new questions. Each answer leading deeper into mystery. And gravastars, whether confirmed or refuted in the coming years, are part of this grand adventure. They represent humanity at its best, curious, persistent, unafraid to question everything, willing to follow evidence even to strange conclusions. They remind us why we do science. Not for practical applications, though those eventually come. Not for technological advancement, though that follows. But for understanding. For knowledge. For the sheer joy of figuring out how nature works. Because in the end, what separates humans from other animals is our drive to understand. Our refusal to accept mystery without investigation. Our insistence on asking why and how about everything we encounter. Gravastars are just the latest manifestation of this eternal human quest. A quest that has taken us from caves to cities, from stone tools to spacecraft, from ignorance to enlightenment. A quest that will continue long after we're gone. And somewhere in that future, perhaps centuries or millennia from now, humans, or whatever we've become, will look back at this era and smile. They'll remember when we first asked about gravastars. When we first detected gravitational waves. When we first imaged the shadow of a compact object. They'll see this as a pivotal moment. When humanity took another step toward understanding the cosmos. Just as we look back at Galileo's telescope, Newton's Principia, Einstein's relativity papers. Each generation has its questions, its mysteries, its frontiers. Gravastars are one of ours. And whether they exist or not, the fact that we can conceive of them, model them, test for them, this is remarkable. This is the power of human intellect. The ability to imagine possibilities beyond direct experience. To construct mathematical descriptions of objects we've never seen. To devise tests that can distinguish between subtle alternatives. This is civilization's highest achievement. Not our buildings or our art or our literature, magnificent as these are. But our science. Our systematic investigation of nature. Our collective effort to understand reality. And gravastars, these strange hypothetical objects at the edge of possibility, exemplify this effort. They may turn out to be real. They may turn out to be fantasy. But the search for them, the observations, the calculations, the debates, the discoveries made along the way, this is undeniably real. This is science in action. And it's a beautiful thing to behold. The hunt for gravastars has transformed from theoretical speculation into experimental campaign. Across the globe, telescopes point skyward. Detectors listen for the faintest whispers in spacetime's fabric. Supercomputers churn through petabytes of data, searching for patterns, anomalies, signatures of the impossible made real. Consider the sheer audacity of what we're attempting. We're trying to distinguish between two objects that differ by distances smaller than a proton's width. We're trying to detect echoes lasting milliseconds in signals from billions of years ago. We're trying to see structure on scales where quantum mechanics and gravity wage their eternal battle. This isn't just difficult. It's at the absolute bleeding edge of what's physically possible with current technology. And yet we persist, because the prize is worth it. Understanding whether gravastars exist could unlock the deepest secrets of nature. The electromagnetic spectrum tells only part of the story. For decades, astronomers relied primarily on light, visible, infrared, radio, X-ray. These wavelengths revealed galaxies, stars, nebulae, all the luminous phenomena of the cosmos. But they're blind to the darkest objects. Black holes shine only through their effects on surrounding matter. And gravastars, if they exist, would be similarly dark. Enter gravitational wave astronomy. A completely new sense. Not electromagnetic radiation but ripples in geometry itself. When LIGO made its first detection in 2015, humanity gained the ability to hear the universe in a fundamentally different way. The collision of two black holes, or what we assumed were black holes, produced a signal so clear, so unmistakable, that it announced a new era of astronomy. But here's the twist. Every detection since then has been interpreted through the lens of standard black hole theory. We see a massive compact object. We assume it's a black hole. We fit the data to black hole models. And the fits are good. Excellent, even. But good fits don't prove uniqueness. Multiple models can produce similar signals. A gravastar merger might look almost identical to a black hole merger. The differences exist in subtle details, in the fine structure of the waveform, in the late-time ring-down phase. Detecting these differences requires exquisite precision. LIGO's detectors can measure distance changes smaller than 1/10,000th the diameter of a proton. This is incomprehensible precision. It's like measuring the distance to Alpha Centauri to within the width of a human hair. And yet it may not be enough. The next generation of detectors promises orders of magnitude improvement. The Einstein telescope, proposed for construction in Europe, would be 10 times more sensitive than LIGO. Built underground in a triangular configuration, shielded from seismic noise, operating at cryogenic temperatures to reduce thermal vibrations. It could detect mergers across the entire observable universe. Cosmic Explorer, the American counterpart, would feature arms 40 kilometers long, 10 times longer than LIGO's. At these scales, detector sensitivity increases dramatically. The subtle differences between black holes and gravastars become resolvable. The echoes become clear. The truth becomes accessible. But building these instruments requires vision, funding, political will. They're multi-billion-dollar projects spanning decades. And they compete with other scientific priorities, other societal needs. Convincing governments and populations to invest in fundamental physics research is never easy. Yet history shows such investments pay dividends. LIGO itself was controversial, expensive, risky. Many doubted gravitational waves would ever be detected. The project nearly died multiple times. But persistence paid off, and now we have an entirely new window on the cosmos. The same could happen with gravastar searches. What seems like esoteric physics today could become transformative technology tomorrow. The quantum vacuum states that stabilized gravastars might inspire new materials, new energy sources, new ways of manipulating spacetime. Or they might not. We cannot predict where fundamental research leads. That's precisely why we do it. The unexpected discoveries are often the most valuable. Meanwhile, theorists continue refining gravastar models. Each year brings new papers exploring different configurations, different equations of state, different formation mechanisms. The mathematical landscape of these objects grows richer, more complex, more nuanced. Some researchers investigate gravastar interiors in detail. What happens in that exotic vacuum core? Can we describe it using effective field theory? Do quantum fluctuations create structure on Planck scales? Is there a smooth transition from the shell to the interior, or a sharp boundary? These questions connect to the deepest problems in physics. Quantum gravity, the holy grail of theoretical physics for nearly a century. We know general relativity works brilliantly at large scales. We know quantum mechanics works perfectly at small scales. But they're fundamentally incompatible. Merging them has proven extraordinarily difficult. Gravastars exist precisely where these two theories collide. If we could observe them, if we could measure their properties precisely, they might provide clues about how to reconcile quantum mechanics and gravity. They might be Rosetta Stones for quantum gravity. String theory offers one approach to this problem. In string theory's framework, all particles are vibrations of tiny strings. Gravity emerges naturally from string dynamics. And string theory makes predictions about exotic objects like gravastars. According to some string theorists, gravastars could be stable configurations of strings and branes wrapped in complex topologies. The event horizon is replaced by a horizon-scale structure of quantum strings. Information is encoded holographically on this structure, preserving unitarity without the need for a true singularity. These ideas are beautiful, mathematically rich, and completely untested. String theory operates at energy scales far beyond experimental reach. We cannot build accelerators powerful enough to probe string-scale physics directly. But cosmological observations, including potential gravistar detections, might provide indirect evidence. Loop quantum gravity takes a different approach. Instead of strings, it posits that spacetime itself is quantized at Planck scales. Space is not continuous but composed of discrete quantum units. Gravity emerges from the dynamics of these fundamental quanta. In loop quantum gravity, the singularity problem disappears naturally. When matter collapses, it cannot be compressed beyond a certain density, the Planck density. Quantum geometric effects create a repulsive force, halting the collapse. This sounds remarkably like the gravistar scenario, though the detailed mechanisms differ. If loop quantum gravity is correct, every black hole might actually be a Planck star, a close cousin of gravistars. The observational signatures would be similar: no true event horizon, a surface of extraordinary density, preservation of information. Testing these theories requires observations of the most extreme objects in nature. And that brings us back to gravistars. Whether they exist as pure vacuum condensates, string-based horizonless objects, or Planck stars from loop quantum gravity, the observational challenge is similar. Find the subtle differences distinguishing them from classical black holes. The search extends beyond gravitational waves and electromagnetic observations. Some physicists propose using cosmic rays, high-energy particles bombarding Earth from space. The most energetic cosmic rays have energies exceeding anything we can produce in accelerators. Where do they come from? One possibility: the surfaces of gravistars. When matter strikes a gravistar's shell at relativistic speeds, the collision would release enormous energy. Particles would be accelerated to extreme velocities. Some would escape, traveling across the cosmos, eventually reaching Earth as ultra-high-energy cosmic rays. If this is true, the energy spectrum and composition of cosmic rays might encode information about gravistar properties. By studying cosmic rays in detail, we might indirectly probe these exotic objects. The Pierre Auger Observatory in Argentina, with its array of detectors spanning 3,000 square kilometers, collects data on the highest energy cosmic rays. The telescope array in Utah does the same. Together, they're building a picture of the most violent processes in the universe. Could some of those processes involve gravistars? Possibly. The data is complex, the interpretations uncertain. But it's another line of evidence, another way of searching for these elusive objects. Neutrinos offer yet another window. These ghostly particles barely interact with matter, passing through planets and stars almost unhindered. But in the most extreme environments, supernovae, black hole mergers, perhaps gravistar collisions, neutrinos are produced in vast numbers. IceCube, buried deep in Antarctic ice, detects neutrinos from cosmic sources. When a high-energy neutrino strikes ice, it creates a characteristic pattern of light. By analyzing these patterns, physicists can trace neutrinos back to their sources and infer the physics occurring there. If a gravistar merger or destabilization produces distinctive neutrino signatures, IceCube might detect them. Combined with gravitational wave observations, this multi-messenger astronomy could definitively identify gravistars. The synergy between different observation methods is crucial. No single technique provides conclusive evidence. But when gravitational waves, electromagnetic signals, cosmic rays, and neutrinos all point to the same conclusion, confidence grows. The case becomes compelling. This is how modern astrophysics works. Not through single dramatic discoveries but through patient accumulation of evidence from multiple independent sources. Each measurement constrains the possibilities. Each observation narrows the parameter space. Slowly, truth emerges. Consider the recent history of neutron-star mergers. In 2017, GW 170817 was detected by LIGO and Virgo. Gravitational waves announced the merger. But within seconds, the Fermi satellite detected gamma rays from the same location. Then optical telescopes saw the kilonova, the radioactive afterglow. Then X-rays. Then radio waves. 70 observatories on all 7 continents and in space observed this single event. The combined data revolutionized our understanding of neutron stars, heavy element formation, gamma-ray burst mechanisms. One event, observed comprehensively, yielded more insights than decades of single-wavelength astronomy. Imagine similar comprehensive observations of a gravistar event. If we could capture every aspect, gravitational waves, all electromagnetic wavelengths, neutrinos, cosmic rays, the resulting data set would be unprecedented. We could test gravistar models with exquisite precision. We could distinguish between alternatives. We could potentially solve the mystery definitively. But this requires coordination, preparation, rapid response. When LIGO detects a promising signal, alerts must go out instantly to observatories worldwide. Telescopes must slew to the source location within seconds. Data must be collected before transient phenomena fade. The infrastructure for this exists now, refined over years of practice. But it can always improve. Faster alerts, more telescopes, better coordination between different observer communities. Every improvement increases our chances of capturing that perfect observation, the one that reveals gravistar nature unambiguously. Some physicists argue we should look not at violent merger events but at quiescent objects. Many galaxies harbor supermassive compact objects in their centers. We call them supermassive black holes. But are they? If even a fraction are gravistars, they should exhibit subtle differences in their quiescent emission. The accretion disk structure would differ slightly. The X-ray variability would have different character. The radio emission would show particular patterns. These differences are small, requiring long-term monitoring campaigns. But patience could pay off. By studying multiple galactic centers over years, accumulating vast datasets, patterns might emerge. Statistical analysis could reveal population-level differences between true black holes and gravistars. This approach complements event-based searches. It's less dramatic but potentially more reliable. Rare violent events are exciting but also uncertain, too many variables, too much chaos. Steady observations of quiescent objects provide cleaner data, easier interpretation. The Vera Rubin Observatory, soon to begin operations in Chile, will survey the entire visible sky every few nights. Over a decade, it will create an unprecedented time-domain map of the universe. Every object that varies, moves, or changes will be catalogued. Among those objects will be thousands of galactic centers, millions of compact object candidates. The data volume will be staggering, hundreds of petabytes. Making sense of it will require advanced machine learning algorithms, automated classification, intelligent filtering. But hidden in that data might be the signatures of gravistars. Patterns invisible to human eyes but detectable by properly trained neural networks. The faint statistical fingerprints distinguishing different populations of compact objects. Artificial intelligence is revolutionizing astronomy. Modern telescopes generate more data than humans can possibly analyze manually. Machine learning fills the gap, finding signals in noise, classifying objects, identifying anomalies worth human attention. For Gravistar searches, AI could be transformative. Train neural networks on simulated Gravistar signals. Teach them to recognize subtle features in gravitational waveforms, in light curves, in spectral data. Then unleash them on real observational data. The networks might find what humans miss. They might identify candidate events that don't quite fit standard models. They might reveal patterns we hadn't thought to look for. Of course, AI has limitations. Networks can hallucinate, finding patterns in random noise. They can be biased by their training data. They require careful validation, skeptical evaluation. But as tools for exploration, they're invaluable. The combination of AI and massive datasets might enable population studies impossible by other means. Instead of identifying individual gravastars, which might be vanishingly rare or observationally indistinguishable, we could characterize populations statistically. Do compact objects divide into distinct populations with different properties? Are there correlations between mass, spin, environment, and internal structure? Does the distribution of quasi-normal mode frequencies show unexpected features? Population studies could reveal the presence of gravastars even if individual identification remains elusive. This is a powerful approach, increasingly used across astrophysics. Beyond observations and simulations lies mathematical physics. Pure theory, divorced from immediate experimental constraints, exploring what's possible within the laws of nature as we understand them. Mathematicians and theoretical physicists continue developing the mathematical structure underlying gravistar models. They explore exotic geometries, unusual matter fields, novel boundary conditions. Sometimes these explorations lead to new physical insights. Sometimes they reveal mathematical curiosities with no obvious physical realization. But occasionally, purely mathematical work predicts something later discovered in nature. Dirac's equation predicted antimatter before positrons were observed. Einstein's equations predicted gravitational waves decades before technology could detect them. Black holes themselves were mathematical curiosities for 50 years before becoming observational reality. Perhaps gravastars follow this pattern. Mathematical solutions found decades ago, awaiting experimental confirmation. Or perhaps they're artifacts, mathematically consistent but physically unrealized. Only nature decides. Our job is to ask clearly, listen carefully, and accept the answer whatever it is. The philosophical implications of gravastars extend beyond physics. They touch on epistemology, how we know what we know. On the limits of human perception and understanding. On the relationship between mathematics and reality. We construct mathematical models of nature. These models make predictions. We test predictions against observations. When they match, we gain confidence in the models. But match isn't proof. Models are always approximations, idealizations, simplifications. Gravastars remind us of this. They're plausible according to our current understanding. The mathematics works. The physics makes sense. But do they exist? We don't know. This uncertainty is uncomfortable but necessary. Science progresses by acknowledging what we don't know, not by pretending we know more than we do. Intellectual honesty requires admitting the limits of current knowledge. And those limits are vast. Despite centuries of progress, we understand perhaps 5% of the universe's content. The other 95%, dark matter and dark energy, remains mysterious. We know they exist through gravitational effects, but we don't know what they are. Gravastars might connect to these mysteries. The exotic vacuum inside might relate to dark energy's nature. The objects themselves might constitute some fraction of dark matter. Or they might be completely unrelated. We won't know until we know. Until observations provide definitive answers. Until theory and experiment converge on truth. The search for gravastars exemplifies science at its best and most challenging. It requires bleeding-edge technology, sophisticated mathematical analysis, careful observational work, creative theoretical thinking, international collaboration, long-term funding, patience. It also requires something less tangible but equally important: scientific imagination. The willingness to consider possibilities that seem outlandish. The courage to challenge established paradigms. The intellectual flexibility to follow evidence even when it leads somewhere unexpected. Maverick ideas often fail. Most alternatives to mainstream theories prove wrong. This is fine, expected, part of the process. Science advances by proposing many ideas and ruthlessly eliminating the false ones. Survival of the fittest ideas through experimental selection. But occasionally, the maverick idea proves correct. The outlandish possibility becomes established fact. The fringe theory moves to the mainstream. And science is revolutionized. Will this happen with gravastars? Impossible to say. The jury is still out. The evidence remains ambiguous. The observations continue. What we can say is that the question is worth asking. The possibility is worth investigating. Even if gravastars prove fictional, the search for them advances multiple fields: gravitational wave astronomy, high-energy astrophysics, quantum gravity, computational physics, detector technology. Every search teaches us something. Every null result constrains possibilities. Every false positive teaches us about our instruments and analysis methods. This is the scientific method in action. Not a linear march to truth but a zigzag exploration of possibility space. We try paths. Some lead nowhere. We backtrack and try different routes. Gradually, the landscape becomes familiar. We learn which directions are promising, which are dead ends. Gravastars are one path we're exploring. Where it leads, we'll discover together. The journey itself is valuable regardless of destination. Because ultimately, science isn't about having all the answers. It's about asking good questions and developing methods to answer them. It's about building a systematic understanding of nature, one observation at a time. It's about humanity's collective effort to make sense of the cosmos we inhabit. And in that grand endeavor, every question matters. Every mystery is worth investigating. Every puzzle piece, however small, contributes to the larger picture. Gravastars may be real or imaginary. Deadly or benign. Common or vanishingly rare. We'll learn which through patient observation, careful analysis, honest evaluation of evidence. And when we do learn the truth, whatever it turns out to be, we'll be wiser for the journey. We'll understand more about collapsed stars, quantum gravity, space-time structure, nature's extreme behavior. We'll have pushed the boundaries of knowledge a little further into the unknown. And that's what science is all about. The human stories behind the Gravastar hypothesis reveal as much about science as the physics itself. Pavel Mazur and Emil Motola weren't working in ivory towers isolated from reality when they proposed their radical idea. They were physicists wrestling with genuine problems in general relativity, trying to resolve contradictions that had bothered theorists for decades. Mazur, a relativist with deep mathematical intuition, had spent years thinking about the endpoint of gravitational collapse. He wasn't satisfied with singularities. The mathematics was clean, yes, but physically, something felt wrong. Nature shouldn't require infinities to describe real objects. Motola brought expertise in quantum field theory, particularly in curved spacetime. He understood how vacuum behaves under extreme conditions, how phase transitions occur, how quantum effects might modify classical predictions in dramatic ways. Their collaboration combined two perspectives that rarely intersect. Relativists and quantum field theorists often speak different languages, work on different problems, publish in different journals. Bridging this divide isn't easy. It requires intellectual flexibility, willingness to learn unfamiliar formalisms, patience with different conceptual frameworks. When they finally published their Gravastar proposal, reactions were mixed. Some colleagues found it intriguing, worth exploring further. Others dismissed it as speculation untethered from observational reality. Still others simply ignored it, absorbed in their own research programs. This is typical for radical new ideas in physics. They don't immediately transform the field. They percolate slowly through the community. A few researchers pick them up, develop them further. Gradually, if the ideas have merit, they gain traction. For Gravastars, this process took years. The first papers attracted modest attention. Then others began publishing extensions, modifications, alternative formulations. The idea spread, mutated, evolved. A small but dedicated community of Gravastar researchers emerged. These researchers faced challenges beyond the scientific. Funding agencies prefer safe bets, established research programs with clear payoffs. Proposing to search for speculative objects that might not exist is risky. Grant applications get rejected. Careers stall. Young scientists especially face difficult choices. Working on mainstream problems offers security, established mentorship, clear career paths. Working on speculative ideas like Gravastars means uncertainty, fewer job opportunities, potential marginalization. Yet some choose this path anyway. Driven by curiosity, by conviction that the idea deserves investigation, by refusal to accept conventional wisdom without challenge. These are science's pioneers, its explorers, its risk-takers. Not all succeed. Some spend careers pursuing ideas that prove fruitless. Their contributions fade into obscurity, remembered only as footnotes in the history of failed hypotheses. This is the harsh reality of frontier research. But others occasionally strike gold. They pursue unfashionable ideas that eventually prove correct. Their early papers, initially ignored, become citation classics. Their perseverance pays off in recognition, prizes, vindication. We don't yet know which category Gravastar researchers fall into. History will judge. But regardless of outcome, their work contributes to the scientific process. They're exploring possibility space, testing alternatives, refusing to accept easy answers. This intellectual courage deserves respect even when the specific ideas prove wrong. The sociology of scientific communities plays a crucial role in determining which ideas flourish and which languish. Science isn't purely objective. It's conducted by humans with biases, preferences, career pressures. The institutions of science, journals, conferences, funding agencies, shape research directions through their decisions about what to publish, spotlight, fund. For Gravastars, breaking into mainstream consciousness required persistent effort. Papers had to pass peer review, sometimes facing skeptical referees convinced the ideas were too speculative. Conference talks had to convince audiences to take the concept seriously. Grant proposals had to persuade reviewers that resources would be well spent. Each step presented obstacles. Not insurmountable, but real. The path from fringe speculation to respectable research program is long and uncertain. What helped Gravastars gain traction was the broader context of problems in black hole physics. The information paradox remained unsolved, troubling many physicists. The singularity problem continued to bother theorists. Alternative proposals to black holes addressed genuine concerns. When LIGO began detecting gravitational waves, suddenly the question became experimentally relevant. These weren't merely abstract theoretical musings anymore. They were testable hypotheses about real objects producing observable signals. This transformed the discourse. Ideas that might have remained purely theoretical became part of observational astronomy. The question shifted from, could gravastars exist mathematically, to, do gravastars exist in our universe? This is a crucial transition. Testability distinguishes science from philosophy. When ideas become testable, they enter the realm of empirical investigation. They can be confirmed or refuted through observation. Not immediately, not easily, but in principle. And that, in principle, matters enormously. The technical challenges of detecting gravastar signatures are formidable. Consider gravitational wave echoes, one of the most promising discriminants. When gravitational waves from a merger hit a reflective surface, they bounce back. These echoes arrive milliseconds after the main signal, carrying information about the reflecting surface's properties. But milliseconds is incredibly short. LIGO samples data at 16,384 Hz, about once every 60 microseconds. Echoes might span only dozens of samples. And they're buried in noise, random fluctuations from seismic activity, thermal vibrations, quantum uncertainties in the detector itself. Extracting meaningful echoes from this noise requires sophisticated signal processing. Matched filtering, where you correlate data with theoretical templates. Bayesian analysis, weighing different hypotheses against evidence. Machine learning, training algorithms to recognize subtle patterns. Each method has strengths and weaknesses. Matched filtering works beautifully if you know what to look for, if your templates accurately model reality. But if gravastar echoes differ from theoretical predictions, due to complexities we haven't modeled, matched filtering might miss them. Bayesian analysis accounts for uncertainties systematically but requires choosing priors, initial probability distributions. Different priors can lead to different conclusions, introducing subjectivity. Machine learning can find unexpected patterns but also generates false positives. Neural networks are sophisticated pattern-matching machines, and they'll match patterns even in pure noise if trained inappropriately. Navigating these challenges requires careful methodology, cross-validation, conservative interpretation. When researchers claim possible echo detections, the community responds with rigorous scrutiny. Are the statistical significance calculations correct? Could instrumental artifacts explain the signals? Have all systematic errors been accounted for? This is healthy skepticism, not obstruction. Science advances when claims are tested rigorously, when alternative explanations are explored thoroughly. Premature acceptance of weak evidence helps no one. Several claimed echo detections have been published, each met with counterarguments. Some researchers present evidence for echoes in certain events. Others reanalyze the same data and find no significant echoes, only noise fluctuations. The debates continue in journal pages and conference halls. This is science working as designed. Multiple groups independently analyzing data. Transparent methodology allowing others to reproduce or challenge results. Gradual convergence toward truth through collective effort. Eventually, consensus emerges. Either echoes become unambiguously detected, reproduced across multiple events by multiple groups, with statistical significance too strong to dispute. Or the evidence remains marginal, explained away by known systematic effects, and the community concludes no reliable echo detections exist yet. We're currently in the uncertain middle phase. Tantalizing hints but no definitive proof. This phase can last years or decades. It requires patience, continued observation, technological improvements. Similar stories play out across astrophysics. Dark matter detection efforts have produced numerous candidate signals over decades, each eventually explained by mundane processes or shown to be instrumental artifacts. Yet the search continues because dark matter definitely exists. Gravitational evidence is overwhelming. Gravastars are different. We don't know they exist. We're looking for something that might be there or might not. This makes the search simultaneously more speculative and more exciting. Discovery would be revolutionary. Non-discovery simply means objects are rarer than hoped, or our detection methods insufficient. Either way, the effort advances detector technology, data analysis techniques, theoretical understanding. The journey is productive regardless of destination. Beyond gravitational waves, other observational avenues continue developing. X-ray astronomy has revealed spectacular phenomena around compact objects. Accretion disks spiraling into black holes, or what we assume are black holes, shine brightly in X-rays. The disk's inner edge location depends on whether there's an event horizon or solid surface. With black holes, matter can orbit arbitrarily close before plunging through the horizon. The innermost stable circular orbit depends on the black hole's spin but not on the presence of a surface. With gravastars, matter cannot penetrate the surface. It must interact with the incredibly dense shell material. This interaction would produce distinctive signatures, boundary layers, shock heating, surface emission. The innermost orbit location would differ from black hole predictions. Current X-ray telescopes lack resolution to see these fine details clearly. But next-generation instruments promise dramatic improvements. Athena, the European X-ray observatory planned for the 2030s, will have unprecedented sensitivity and spectral resolution. It could potentially distinguish between black hole and gravastar accretion signatures. The Japanese RISA mission, launched in 2023, provides a preview of what's coming. High-resolution X-ray spectroscopy reveals details of gas motion, temperature, density near compact objects. The iron K-alpha line, a characteristic emission from iron atoms, is particularly informative. Its shape and position encode information about spacetime curvature, gas motion, gravitational redshift. If gravastars exist, their iron line profiles should differ subtly from black holes. The differences are small, requiring long observations of bright sources. But they're potentially measurable. This exemplifies modern observational astrophysics, patient accumulation of high-quality data, sophisticated modeling, careful comparison with theoretical predictions. No single observation proves anything. But dozens of consistent measurements build a compelling case. Radio astronomy contributes its own insights. Very long baseline interferometry, linking radio telescopes across continents, achieves astonishing angular resolution. The Event Horizon Telescope demonstrated this spectacularly, imaging the shadow of M87's central object. Future expansions of EHT, adding telescopes in Africa and Asia, will improve coverage and resolution. Space-based radio telescopes, proposed for future missions, would extend baselines beyond Earth, achieving even finer resolution. With sufficient resolution, we might distinguish event horizon from solid surface. The photon sphere, where light orbits the compact object, has different structure depending on what lies beneath. A black hole's horizon absorbs photons. A gravastar's surface reflects them, though enormously redshifted. These reflected photons could, in principle, contribute to observable emission. Sophisticated radiative transfer calculations predict what we should see in different scenarios. The predictions differ subtly between black holes and gravastars. Observers compare data with predictions, using Bayesian model comparison to assess which scenario better fits observations. Current data is consistent with both, unable to distinguish definitively. But improved resolution and sensitivity will narrow the possibilities. The interplay between theory and observation here is intricate. Theorists predict observational signatures. Observers search for them. If found, theories gain support. If not found, theories are constrained or rejected. This feedback loop drives progress. For gravastars, the loop is still turning. Predictions exist. Searches continue. Definitive results await better data. Meanwhile, theoretical work explores increasingly exotic variations. Rotating gravastars present particular challenges. Angular momentum affects stability in complex ways. Centrifugal forces want to tear the object apart. Internal pressure must balance not just gravity but also rotation. The mathematics becomes fearsome. Exact solutions rarely exist. Numerical simulations are essential. And simulations require assumptions about matter properties at Planck density, properties we don't truly know. Different assumptions lead to different stability conclusions. Some models show rotating gravastars can be stable across wide parameter ranges. Others find stability only in narrow regions. Still others suggest rotation inevitably destabilizes these objects. Resolving these questions requires better understanding of quantum gravity. Until we have a complete theory of how spacetime behaves at Planck scales, uncertainties remain. This is frustrating but unavoidable. We're pushing against the boundaries of known physics. Some questions cannot be answered definitively with current knowledge. We do the best we can, acknowledge uncertainties clearly, and hope future theoretical breakthroughs provide answers. Quantum gravity remains physics's greatest unsolved problem. 90 years after quantum mechanics formulation, we still cannot consistently combine it with general relativity. The theories are fundamentally incompatible in their current forms. Many approaches have been tried. String theory, loop quantum gravity, asymptotic safety, causal dynamical triangulations, noncommutative geometry. Each has insights, mathematical beauty, dedicated proponents. None has definitive experimental confirmation. Gravastars might provide the experimental handle quantum gravity desperately needs. If we can observe these objects precisely enough, we might test quantum gravity predictions directly. Different quantum gravity theories make different predictions about gravastar stability, structure, observational signatures. This is why gravastar research matters beyond the specific question of whether these objects exist. It's a window into quantum gravity, the deepest layer of physical reality. Consider how previous astronomical observations transformed physics. Before the 20th century, physics was classical, Newton's laws, Maxwell's equations, thermodynamics. The universe seemed deterministic, continuous, comprehensible. Then observations forced revisions. Blackbody radiation curves didn't match classical predictions. Atomic spectra showed discrete lines, not continuous spectra. The photoelectric effect violated classical expectations. These anomalies led to quantum mechanics. A complete revolution in how we understand reality. And it started with careful observations that didn't fit theories. Might gravastars play a similar role? Could their detailed observations force revisions to general relativity, to quantum field theory, to our understanding of spacetime? Possibly. History doesn't repeat but it rhymes. Scientific revolutions often begin with observations that don't quite fit existing frameworks. Of course, most anomalies don't trigger revolutions. Most are eventually explained within existing theory, or turn out to be experimental errors. Distinguishing truly revolutionary observations from mundane oddities is nearly impossible in real time. Only retrospectively, after new theories are formulated and confirmed, do we recognize which observations were pivotal. In the moment, everything is uncertain, ambiguous, contested. This is why maintaining multiple research programs matters. We don't know which ideas will prove fruitful. Supporting diverse approaches increases the chances that someone finds the right path. For gravastars, this means funding continued theoretical work even without observational confirmation. It means building detectors sensitive enough to see the subtle differences. It means training students in the necessary skills. It means fostering communities where unconventional ideas can be discussed seriously. Science requires infrastructure, not just physical equipment but intellectual infrastructure. Journals willing to publish speculative papers. Conferences with sessions on alternative theories. Funding programs supporting high-risk research. Universities employing researchers working on unfashionable problems. This infrastructure is always under pressure. Resources are limited. Conventional programs produce steady results. Speculative programs might produce nothing. The temptation to focus on safe bets is strong. But science cannot advance without risk-taking. Breakthroughs come from unexpected directions. If everyone works on incremental improvements to established theories, paradigm shifts become impossible. Balance is essential. Most research should be conventional, building on solid foundations. But some fraction must explore alternatives, challenge orthodoxy, investigate radical possibilities. Gravastars represent that exploratory fraction. They might revolutionize our understanding. They might prove irrelevant. The uncertainty is precisely why they deserve investigation. The economics of big science present peculiar challenges. Modern astrophysics requires billion-dollar instruments. LIGO cost over $1 billion to build and operate. LISA will cost billions more. The Einstein telescope, if built, will cost several billion euros. These sums are enormous by academic standards, tiny by government standards. A single military aircraft costs more than LIGO. A few kilometers of highway equal LISA's price tag. Yet securing funding for fundamental science is always difficult. Taxpayers reasonably ask, why spend billions on abstract questions when earthly problems demand attention? Politicians need to justify expenditures to skeptical constituents. The answers are rarely simple. Long-term benefits of fundamental research are real but unpredictable. GPS wouldn't exist without relativity, developed with no practical application in mind. Quantum mechanics, purely theoretical when formulated, now underlies most modern technology. But these connections aren't obvious. They emerge decades after initial discoveries. Promising near-term applications usually oversell science's immediate utility. Honest advocates acknowledge uncertainty. We don't know what applications might emerge from quantum gravity research. We don't know if Gravastar discoveries would enable new technologies. We pursue these questions because they're fundamental, because understanding nature deeply is valuable in itself. This argument works with some audiences. It fails with others. Science funding therefore involves not just scientific merit but political skill, public communication, coalition building. Researchers increasingly recognize this. They engage with public outreach, explaining their work to non-specialists. They write popular articles, give public lectures, create YouTube videos. They make science accessible, exciting, relevant. This is time-consuming, often unrewarded by academic promotion committees. But it's essential for maintaining public support. Society funds science. Scientists must explain to society why their work matters. For Gravastars specifically, the outreach challenge is significant. These are abstract concepts requiring substantial background to understand. Communicating them requires careful balance between accuracy and accessibility. Too technical, audiences tune out. Too simplified, the actual content disappears. Finding that sweet spot demands skill, practice, feedback. Some scientists excel at this. They craft narratives that capture imagination while respecting complexity. They use analogies, metaphors, thought experiments to convey abstract ideas. They acknowledge uncertainties honestly while conveying excitement about possibilities. Others struggle. Not every brilliant researcher is a gifted communicator. This is fine, division of labor makes sense. But the scientific community collectively must ensure its work is communicated effectively. As Gravastar research progresses, communicating results to broader audiences becomes increasingly important. If definitive evidence emerges, the world should understand what's been discovered. If searches continue yielding ambiguous results, public patience requires explaining why the question remains worth pursuing. Science communication is not mere translation of technical papers into plain language. It's storytelling, crafting narratives that help people understand not just what we've learned but why it matters, how we learned it, what questions remain. The Gravastar story is rich with narrative potential. The mystery of what happens when stars die. The paradoxes haunting black hole physics. The audacious proposal of alternative structures. The painstaking search using cutting-edge technology. The gradual accumulation of evidence. The uncertainties and debates. This is dramatic, compelling, human. It's not just equations and observations but a quest for understanding, an intellectual adventure unfolding over decades. Telling this story well could inspire the next generation of physicists. Young people need to see science as exciting, creative, challenging. Not just memorizing facts but wrestling with deep questions, constructing and testing theories, exploring the unknown. Gravastars exemplify this. They're frontier research where fundamental questions remain open. Where clever ideas matter as much as expensive equipment. Where a graduate student with a good insight can make meaningful contributions. This accessibility is important for field health. If only massive collaborations at billion-dollar facilities can do meaningful work, opportunities narrow. But when theoretical and computational research can still make progress, talented individuals worldwide can participate. Gravastar research remains partially in this accessible regime. Important work happens through numerical simulations on university clusters. Through analytical calculations performed with pencil and paper. Through novel analysis of publicly available data. Not everything requires LIGO or LISA. Individual researchers and small groups can contribute meaningfully. This democratization of research opportunities is valuable, sustaining diverse participation. Of course, definitive observational answers ultimately require major facilities. But framing questions, developing analysis techniques, predicting signatures, this work happens broadly across the community. The community itself is fascinatingly diverse. Relativists, quantum field theorists, astrophysicists, computational physicists, observational astronomers. People trained in different disciplines, bringing different tools and perspectives. This diversity strengthens research, preventing groupthink, encouraging creative approaches. Interdisciplinary work is challenging. Different fields have different standards, different jargon, different implicit assumptions. Bridging these differences requires effort, patience, mutual respect. But the payoff is substantial. Problems that seem intractable from one perspective yield to tools from another. Observations that confuse astronomers clarify through theoretical analysis. Theoretical puzzles find resolution through computational exploration. Gravastars demand this interdisciplinary approach. No single perspective suffices. Understanding these potential objects requires integrating relativity, quantum physics, astrophysical context, observational capabilities. This integration is where science becomes art. Weaving together disparate threads into coherent tapestry. Seeing connections others miss. Asking questions that cut across traditional boundaries. The best science often happens at disciplinary boundaries. Where established methods of one field meet unresolved problems of another. Where fresh eyes see possibilities entrenched specialists overlook. Gravastars emerged at such a boundary. Between relativity and quantum field theory. Between astrophysical observation and mathematical physics. This boundary location made them easy to miss initially but increasingly central as different fields converged. As gravitational wave astronomy matures, as detector sensitivity improves, as theoretical understanding deepens, gravastars move from fringe speculation toward mainstream inquiry. They're not yet established but no longer easily dismissed. This trajectory, from wild idea to serious research topic, is worth studying. It reveals how scientific consensus forms, how communities evaluate novel proposals, how frontier concepts gain or lose credibility. The process isn't always rational. Social factors matter. Who proposes ideas influences how they're received. Ideas from prestigious researchers at elite institutions get more attention than identical ideas from unknown researchers at obscure universities. This is unfortunate but human. Reputation and social capital matter in science as in all human endeavors. Complete objectivity is impossible when humans do the judging. But science has self-correcting mechanisms. Over time, evidence accumulates. Good ideas supported by data gain acceptance regardless of source. Bad ideas fail regardless of who proposes them. The timeline varies, but truth eventually emerges. For gravastars, we're watching this process unfold. The hypothesis has circulated for 2 decades. It's gained adherence, spawned research programs, generated testable predictions. But it hasn't yet achieved consensus acceptance. The next decade will be crucial. LIGO and Virgo continue collecting data. LISA's launch approaches. New telescopes come online. Detector sensitivity improves. Analysis techniques refine. By 2035, we'll likely know much more. Either gravastar evidence will be compelling, or continued null results will push the hypothesis toward obscurity. Either way, clarity will emerge from current ambiguity. This is the exciting phase, where real progress happens, where uncertainty resolves into knowledge. Being present for this transition, contributing to it, witnessing it unfold, this is the privilege of contemporary researchers. Future historians of science will look back at this era, analyzing how the gravastar question was resolved. They'll read papers, conduct interviews, trace intellectual lineages. They'll construct narratives explaining how understanding developed. But we're living it. We don't know how the story ends. This immediacy, this authentic uncertainty, makes the experience thrilling. Every new gravitational wave detection brings possibilities. Could this be the one? Could these echoes be unambiguous? Could this merger finally reveal gravastar nature definitively? So far, no. But the next event might. Or the one after. Hope persists because the possibility remains real. The environment surrounding a gravastar would be a laboratory of extreme physics unlike anything we've seen. Consider the space-time geometry near the surface. Curvature approaches but doesn't reach the critical value for horizon formation. This creates a region where relativistic effects dominate everything. Time dilation near the surface becomes extreme. An observer hovering just above a gravastar's shell would experience time flowing at a tiny fraction of the rate experienced by distant observers. 1 second near the surface could equal years, decades, centuries in the external universe. This isn't hypothetical abstraction, it's a direct consequence of Einstein's equations, confirmed countless times in less extreme scenarios. What does this mean for matter falling toward the gravastar? As it approaches, it appears to slow down from the perspective of distant observers. Not because forces are restraining it, but because time itself is running slower. Photons escaping from near the surface are enormously redshifted, their wavelength stretched by the intense gravitational field. This creates observational challenges. Emissions from the surface or near-surface region would be redshifted into invisibility in many cases. High-energy X-rays become infrared. Ultraviolet becomes radio waves. The entire electromagnetic spectrum shifts downward, making detection difficult. But also opportunities. If we can detect these heavily redshifted emissions, we can probe the extreme environment directly. The degree of redshift encodes information about the gravitational field strength, which depends on the object's structure. For a black hole, redshift approaching the horizon becomes infinite, light can barely escape, and from the horizon itself, not at all. For a gravastar, redshift near the surface becomes enormous but remains finite. There's a difference, subtle but measurable with sufficiently sensitive instruments. Magnetic fields complicate the picture beautifully. Compact objects often possess powerful magnetic fields, remnants from their progenitor stars compressed into tiny volumes. Field strengths near neutron stars reach trillions of Gauss, quadrillions of times Earth's field. Gravastars could harbor similarly intense fields. These fields would thread through the accretion disk, channeling matter, accelerating particles to relativistic energies, generating jets of plasma shooting outward at near-light speeds. The interaction between magnetic fields and the gravastar surface would differ from black hole magnetospheres. With a solid surface, fields can anchor to the material. They can twist, reconnect, trigger explosive releases of magnetic energy. These magnetically powered flares could be distinctive signatures, different from black hole systems. Studying variability patterns in X-ray emission might reveal these differences. Black hole systems show quasi-periodic oscillations with particular frequency relationships. Gravastar systems might show different patterns, reflecting the different boundary conditions at the surface versus horizon. This is detective work at the highest level. Taking fragmentary observations, light curves, spectra, timing data, and inferring the nature of objects millions or billions of light-years distant. It requires sophisticated modeling, careful statistics, exhaustive consideration of alternatives. Current data remains insufficient for definitive conclusions. But each observation adds information. Each measurement constrains parameters. Slowly, the parameter space shrinks. Eventually, only one possibility remains consistent with all data. We're far from that point with gravastars. Multiple scenarios remain viable. But the trajectory is clear: more data, better instruments, refined models. Convergence is inevitable, even if slow. The lifetime of a gravastar presents fascinating questions. Black holes are remarkably stable. Once formed, they can persist essentially forever, slowly evaporating via Hawking radiation on timescales vastly exceeding the universe's current age. A stellar mass black hole would take 10 to 67 years to evaporate completely, inconceivably longer than the universe's 13.8 billion year age. Gravastars, with their exotic internal structure, might behave differently. The vacuum phase transition that stabilizes them could be metastable, stable against small perturbations but vulnerable to tunneling into a lower energy state over vast timescales. Quantum tunneling allows systems to transition between states even when classical physics forbids it. A ball sitting in a valley can quantum mechanically tunnel through the mountain into a deeper valley. The probability is typically minuscule, but over cosmological timescales, even minuscule probabilities become relevant. If the gravastar configuration is metastable, every gravastar is essentially a ticking clock. Eventually, randomly, quantum fluctuations will trigger a phase transition. The exotic vacuum will decay. The structure will collapse or explode. The timescale for this depends on details of the quantum field theory describing the vacuum. It could be longer than the universe's age. Could be shorter. We don't know without better understanding of Planck scale physics. This uncertainty makes population predictions difficult. If gravastars decay rapidly, few ancient ones would remain. If they're truly stable, primordial gravastars from the early universe could still exist. Observing the gravastar mass distribution could provide clues. If old gravastars decay preferentially, we'd expect to see mostly young systems. If age doesn't matter, the distribution would reflect formation history. Of course, distinguishing gravastar age from black hole age observationally is nearly impossible. We can't directly measure how long a compact object has existed. We can only infer age from environmental clues, stellar populations nearby, galaxy properties, cosmological redshift. These indirect methods have large uncertainties. But they're what we have. Astrophysics often requires extracting maximum information from minimal data. The formation mechanisms for gravastars remain contentious. If they exist, how do they form? Do all sufficiently massive stars produce gravastars instead of black holes? Only stars with specific properties? Or do gravastars form through completely different processes? One possibility: direct collapse in the early universe. In the first hundreds of millions of years after the Big Bang, the universe contained no heavy elements. Stars formed from pure hydrogen and helium, fundamentally different from modern stars rich in heavier elements. These primordial stars could be incredibly massive, hundreds or thousands of solar masses. When such monsters collapsed, conditions might favor gravastar formation over black hole formation. The physics differed from contemporary stellar collapse due to different compositions, different rotation rates, different magnetic field properties. If primordial gravastars formed in significant numbers, they could constitute dark matter. They'd be invisible. No nuclear fusion means no light, but gravitationally influential. They'd cluster with normal matter, affecting galaxy formation, contributing to the dark matter halos observed around galaxies. Detecting primordial gravastars would be extraordinarily difficult. They're dark, compact, potentially scattered across the universe. Only through gravitational effects could we find them. Microlensing surveys, which detect compact objects when they pass in front of background stars and briefly brighten them through gravitational lensing, might discover them. Several microlensing surveys operate currently. OGLE in Chile has discovered thousands of lensing events. MOA in New Zealand complements it. These surveys were designed to search for planets, brown dwarfs, stellar remnants. But they're also sensitive to more exotic objects like primordial gravastars. So far, the lensing event distribution seems consistent with ordinary compact objects, white dwarfs, neutron stars, stellar mass black holes. No compelling evidence for a novel population exists. But the data isn't conclusive. Subtle differences might exist that careful analysis would reveal. Future surveys will dramatically expand sensitivity. The Vera Rubin Observatory will monitor hundreds of millions of stars simultaneously, detecting far more lensing events. Machine learning algorithms will comb through data, identifying unusual patterns worth detailed investigation. If a significant primordial gravastar population exists, these surveys should find hints. Population statistics would show anomalies. Mass distributions would differ from expectations. Spatial distributions might reveal unexpected clustering. This is statistical astronomy at scale. Individual events prove little. But aggregate patterns over millions of observations can reveal truths invisible in smaller samples. Another formation channel, mergers. When two neutron stars merge, they create a hypermassive object, temporarily supported against collapse by rapid rotation. This object is unstable, and within seconds to hours, it must collapse. Standard theory predicts black hole formation. But if the conditions are right, might a gravastar form instead? The merger environment is extraordinarily complex. Matter is heated to trillions of degrees. Densities exceed nuclear density. Magnetic fields are amplified to extreme values. In this chaos, could quantum effects trigger the vacuum phase transition? Could the system find the gravastar configuration rather than collapsing to a black hole? Some theorists argue yes. The merger provides an opportunity for novel physics to manifest. Testing this requires detailed simulations. Modeling neutron star mergers challenges even the most powerful supercomputers. The physics spans enormous ranges, from kilometer scales down to atomic scales, from microseconds to hours, from nuclear physics to general relativity. Current simulations make approximations. They must. Perfect simulations are impossible. But as computational power increases, as algorithms improve, simulations become more realistic. They can incorporate more physics, resolve finer details, run longer. If merger-produced gravastars are possible, simulations should eventually show them. The code would predict specific conditions leading to gravastar versus black hole formation. Observational searches could then target mergers meeting those conditions. GW170817, the neutron star merger detected in 2017, provided a wealth of data. The gravitational wave signal, electromagnetic counterparts across all wavelengths, timing of different emissions. All of this constrains what happened when those stars merged. The data is consistent with black hole formation, but also with several alternative scenarios, including potentially gravastar formation. The degeneracy between models frustrates definitive interpretation. Future detections with better sensitivity might break this degeneracy. If we can observe the late-time behavior more clearly, see how the remnant settles or oscillates, measure its properties more precisely, we can distinguish between alternatives. Each merger provides a natural experiment. Nature sets up the conditions. We observe the results. Collectively, dozens or hundreds of merger observations will constrain formation physics powerfully. This is a long game. Individual events provide limited information. But patterns emerging from many events reveal underlying physics. Patience is required, but the payoff is understanding how these extraordinary objects come into existence. The chemical enrichment history of galaxies could encode gravastar signatures. When massive stars explode as supernovae, they scatter heavy elements into space. These elements incorporate into new stars, planets, eventually living organisms. We are made of stardust, literally. But compact object formation mechanisms affect which elements are produced and in what quantities. Black hole formation versus gravastar formation versus direct supernova might leave different chemical fingerprints in galactic composition. If gravastars form frequently, they might retain more matter rather than ejecting it in explosions. This could alter the relative abundances of various elements compared to expectations from standard stellar evolution models. Galactic archaeology, reconstructing galaxy history from current composition, might reveal these effects. If observed element ratios don't match predictions from standard models, exotic formation channels like gravastars could explain discrepancies. This is indirect, circumstantial evidence. Many factors affect galactic chemistry. Disentangling them requires careful modeling, accounting for countless processes. But anomalies in chemical evolution could point toward non-standard compact object formation. The most metal-poor stars, ancient stars born when the universe was young, provide particularly valuable clues. Their compositions reflect enrichment from the very first stellar generations. If those early stars produced gravastars rather than black holes, the chemical signatures should differ detectably. Surveys like SDSS and Gaia have cataloged millions of stellar spectra. Data mining these archives for anomalous chemical patterns is ongoing. Most anomalies will have conventional explanations. But occasionally, something genuinely new emerges from big data. Gravastars would participate in dynamical processes within galaxies. Dense stellar environments like globular clusters contain thousands of stars in compact volumes. Interactions are frequent. Compact objects can collide, merge, be ejected at high velocities. If some compact objects are gravastars rather than black holes, dynamical evolution would differ subtly. Interaction cross-sections might differ. Energy transfer during close encounters would vary. Over millions of years, these small differences accumulate into observable effects. Globular cluster dynamics are complex. N-body simulations tracking individual stars require immense computation. But they're feasible now for modest-sized clusters. These simulations can test whether gravastar populations would produce different cluster evolution than pure black hole populations. Results so far are inconclusive. The differences are small, often within simulation uncertainties. But as techniques improve, as longer time spans are simulated, distinguishing features might emerge. Globular clusters also harbor low-frequency gravitational wave sources, compact object binaries spiraling over millions of years. Future space-based detectors like LISA will observe these systems. Their properties encode information about the compact object population. If gravastars are present, the binary population statistics should show distinctive features. Mass ratios, orbital parameters, merger rates, all would differ from pure black hole populations. LISA data will constrain these statistics, providing another independent test. The gravitational wave background, the incoherent sum of all unresolved sources throughout cosmic history, might also carry gravastar signatures. This background is like the cosmic microwave background but for gravitational waves. A faint hum pervading spacetime, containing information about countless sources too distant or too weak to resolve individually. LIGO is beginning to detect hints of this background. As sensitivity improves, the background will become clearly measurable. Its spectrum, How gravitational wave power distributes across frequencies depends on the source populations throughout cosmic history. If gravastars were common in the early universe, they'd contribute to the background differently than black holes. Their distinct merger characteristics would create different spectral features. Measuring the background precisely could reveal the presence of non-standard compact objects. This is archaeology through gravitational waves. The background encodes history. By decoding it, we reconstruct the past. We learn what processes operated when, how frequently, with what properties. It's like paleontology but for spacetime itself. We're excavating ancient gravitational fossils, reading the universe's history written in ripples of geometry. The philosophical implications of gravastar existence extend into metaphysics. If these objects are real, they challenge our concepts of inside and outside, surface and interior. A black hole has no surface in the conventional sense. The event horizon is not a physical boundary but a mathematical surface in spacetime, a point of no return. There's no stuff there, no material boundary. It's pure geometry. A gravastar has a genuine surface, physical and material. Yet that surface is so thin, potentially a Planck length, that it challenges our notion of what surface means. Can something 1 Planck length thick meaningfully be called a surface? Or is it something else entirely, a quantum geometric structure without classical analog? These questions aren't merely semantic. They touch on deep issues about the nature of physical reality at fundamental scales. What exists when we push to the smallest possible distances? What do spatial concepts like boundary or interior mean when quantum effects dominate? Physics typically deals with operational definitions. A surface is whatever reflects particles or absorbs them. An interior is whatever lies within a boundary. These definitions work perfectly at human scales and even down to atomic scales. But at Planck scales, operational definitions become problematic. We cannot operationally probe distances smaller than a Planck length. We cannot measure positions with such precision. The Heisenberg uncertainty principle forbids it. So when we speak of a gravastar's Planck-thick shell, we're extrapolating concepts beyond their operational regime. We're doing metaphysics disguised as physics. This doesn't make the discussion meaningless. Metaphysical questions often drive physics progress. Asking, what is space, or what is time, sounds metaphysical, but it led Einstein to relativity. Asking, what is simultaneously, led to understanding relativity's core. Similarly, asking, what is a surface at Planck scales, might lead to insights about quantum gravity. The question forces us to think carefully about how classical geometric concepts emerge from quantum substrate. Gravastars are thought experiments made potentially real. They're conceptual probes of physics boundaries. Whether or not they exist physically, thinking clearly about them advances understanding. The relationship between mathematics and physical reality remains mysterious. Mathematics works unreasonably well for describing nature. Equations written by theorists, motivated by mathematical beauty or logical consistency, turn out to describe real phenomena with extraordinary accuracy. Why? Why does the universe speak mathematics? This is one of physics' deepest mysteries. Gravastars exemplify this mystery. They emerged from mathematical solutions to Einstein's equations. Mathematicians and theoretical physicists explored solution space, finding configurations satisfying the equations. These configurations had no observational motivation initially. Pure mathematical exploration. Yet these mathematical objects might be physically real. Mathematics predicted their possibility before any observational hint existed. If confirmed, this would be another triumph of mathematics' predictive power. But it would also raise questions. How does mathematics know about physical reality? Why do abstract mathematical structures correspond to concrete physical objects? Some physicists embrace Platonism, the idea that mathematical structures have independent existence, and physical reality is somehow realized mathematics. Others prefer constructivism, mathematics is human invention, and its effectiveness is partly anthropic selection. We notice the mathematics that works, ignore what doesn't. These philosophical positions are probably untestable. But they frame how we think about theory development. Are we discovering pre-existing mathematical truths about nature? Or inventing useful descriptions that happen to fit observations? For gravastars, both perspectives have merit. The mathematics was discovered/invented by exploring equation solution space. The physics is checked by comparing predictions with observations. The interplay between mathematical exploration and empirical testing is where knowledge emerges. This interplay is science's essence. Theory without observation is speculation. Observation without theory is stamp collecting. Together, they create understanding. The pace of progress in gravastar research depends on factors beyond pure science. Funding cycles, personnel availability, competing priorities all matter. Science doesn't occur in a social vacuum. Currently, gravastar research occupies a middle tier of attention. It's not fringe, respected researchers publish papers, conferences have sessions, grant proposals sometimes succeed. But it's not mainstream either. The bulk of compact object research assumes black holes. This positioning affects everything. Graduate students interested in gravastars find fewer advisors, fewer positions. Postdocs working on gravastars face competitive job markets. Tenure-track faculty need to balance unconventional research with safer projects producing steady publications. These pressures shape research trajectories. Ambitious projects get scaled back. Risky ideas get deferred. The path of least resistance leads toward mainstream topics. Yet some researchers persist anyway. They find ways to work on questions they find compelling, even at career cost. This persistence is admirable but shouldn't be necessary. Ideally, scientific merit alone would determine research directions. But we don't live in ideal worlds. We live in worlds with limited resources, human biases, institutional inertia. Navigating these realities while maintaining scientific integrity is challenging. For gravastar research to flourish, it needs institutional support. Funding agencies should recognize high-risk, high-reward research. Universities should value diverse research portfolios. Journals should welcome papers challenging conventional wisdom. Some of this is happening. Funding agencies increasingly have programs supporting speculative research. Some journals explicitly encourage controversial papers. Progress occurs, albeit slowly. The alternative is stagnation. If only safe mainstream research gets supported, paradigm shifts become impossible. Science ossifies into normal science, incrementally refining established frameworks without questioning foundations. Gravastars might be wrong. Most alternative theories are. But having some researchers seriously investigating alternatives is healthy for the field. It prevents groupthink, encourages critical evaluation of assumptions, occasionally leads to genuine breakthroughs. Even if gravastars prove non-existent, the research isn't wasted. Techniques developed for searching them apply to other problems. Theoretical insights about exotic vacuum states inform cosmology. Detector improvements benefit all gravitational wave astronomy. This is research's hidden value. Direct applications are unpredictable. But general capabilities developed through research enable future work we can't foresee. LIGO wasn't built to search for gravastars. It was built to detect gravitational waves from black hole mergers. But having built it, we can use it to search for gravastars too. The infrastructure serves multiple purposes. Similarly, any major new detector or telescope enables science beyond its primary mission. This generality argues for ambitious projects even when specific payoffs are uncertain. The technological spillovers from gravitational wave astronomy are significant. LIGO required advances in laser stabilization, vibration isolation, vacuum technology, data analysis. These advances have applications far beyond astrophysics. Medical imaging benefits from signal processing techniques developed for gravitational wave detection. Precision manufacturing improves through vibration isolation technology. Materials science advances through ultra-high vacuum requirements. These spillovers rarely appear in project proposals. They're happy accidents, bonus benefits from pursuing fundamental science. But collectively, they justify major investments in basic research. For gravastars specifically, technological demands are similar to black hole searches. No fundamentally new technology is required. This makes the research relatively low cost compared to detector construction. The major costs are personnel, scientists' time and expertise. But these are modest compared to hardware. A few dozen researchers working on gravastar theory and observations cost perhaps tens of millions annually. A rounding error in major facility budgets. This favorable cost-benefit ratio argues for continued support even absent definitive results. The potential payoff, understanding quantum gravity, resolving black hole paradoxes, discovering new exotic objects, vastly exceeds costs. Of course, resources are finite. Supporting gravastar research means less support for something else. Opportunity costs matter. But the opportunity cost of not investigating alternatives is stagnation. If the black hole paradigm is incomplete, clinging to it exclusively delays progress. Some diversification of research programs is prudent risk management. Ideally, we'd support multiple approaches simultaneously. Black hole research should continue. It's productive and successful. But alternatives like gravastars, boson stars, naked singularities deserve parallel investigation. Not equal resources, mainstream ideas with strong observational support deserve more. But non-zero resources for alternatives, proportional to their plausibility and potential impact. This portfolio approach to research investment makes sense. Like financial portfolios, scientific portfolios benefit from diversification. Some investments fail. Others pay off spectacularly. Maintaining variety increases chances of major breakthroughs. The human element in science cannot be ignored. Discoveries come from people, their creativity, intuition, persistence. Supporting people means more than funding. It means creating environments where creativity flourishes. What environments support creative science? This question has been studied extensively. Some patterns emerge clearly. Intellectual freedom matters enormously. Researchers need autonomy to pursue questions they find compelling, even when these diverge from mainstream or funder priorities. Micromanagement kills creativity. Collaboration helps, but so does solitude. Different people thrive in different environments. Some do best in large teams, others working independently. Rigid structures imposing single working styles limit potential. Interdisciplinary interaction sparks creativity. When experts from different fields collaborate, they bring different tools and perspectives. Fresh combinations of ideas emerge. Tolerance for failure is essential. Most research attempts fail. Most hypotheses prove wrong. Most experiments yield no results. If failure is punished, risk-taking disappears. Only safe incremental work occurs. Long-term stability enables ambitious projects. Constantly scrambling for next grant prevents thinking deeply about hard problems. Some level of sustained support, without excessive justification requirements, allows depth. These principles are well known. Implementing them is challenging. Institutions have inertia. Funding systems have established patterns. Changing them requires political will, which requires public understanding of science's nature. The public largely misunderstands how science works. Movies portray lone geniuses having sudden insights. News reports emphasize breakthrough discoveries. The long, messy, uncertain process of actual research rarely appears. This creates unrealistic expectations. People expect steady progress, dramatic discoveries, immediate applications. When research proves slow, uncertain, with many dead ends, frustration follows. Support wavers. Better science communication could help. Showing research's real nature, uncertain, difficult, often failing but occasionally succeeding spectacularly. Making the process visible, not just results. For Gravastars, communicating the uncertainty is crucial. We don't know if they exist. We're searching, using best available methods. We might find them. Might not. Either outcome advances knowledge. This honest uncertainty might actually engage public interest better than false certainty. People appreciate authenticity. They understand that exploration involves unknowns. Pretending we know more than we do undermines trust. The Gravastar story is genuinely uncertain. That's its appeal. It's real exploration, not verification of known facts. Outcome unknown, stakes high, method sophisticated. It's science in its purest form. Sharing this story widely could inspire the next generation. Young people need to see that science is adventure, not rote memorization. That fundamental questions remain open. That their contributions could matter. Some of today's students will become the researchers who definitively answer the Gravastar question. They'll build better detectors. Run more sophisticated simulations. Develop novel analysis techniques. Make the observations that finally resolve ambiguity. What motivates them toward these careers? Often, early exposure to exciting ideas. Reading about mysteries. Meeting scientists doing cutting-edge work. Realizing that the universe still holds secrets. Gravastars can play that role. They're accessible enough for motivated non-experts to grasp basics. Exotic enough to capture imagination. Uncertain enough to offer opportunities for contribution. This educational value shouldn't be underestimated. Even if Gravastars prove fictional, introducing them to students serves purposes. It teaches about extreme physics, theoretical reasoning, observational astronomy, scientific methodology. These are transferable skills. Not every student becomes an astrophysicist. But those learning to think clearly about complex, uncertain problems become better engineers, doctors, programmers, teachers, citizens. Science education is about more than content. It's about developing reasoning skills, quantitative literacy, epistemological sophistication. Gravastars provide excellent vehicles for developing these capacities. Students can calculate gravitational time dilation near Gravastar surfaces. Analyze actual gravitational wave data searching for echoes. Run simplified simulations exploring stability. Write essays evaluating evidence quality. These activities teach far more than lectures. Active engagement with real problems beats passive content absorption. Modern pedagogy emphasizes this increasingly. For Gravastars, abundant educational opportunities exist. The topic connects relativity, quantum mechanics, astrophysics, observational techniques. It's inherently interdisciplinary, showing how different physics branches integrate. It's also current. Research papers continue publishing. Debates continue. Students can follow real scientific discussions, seeing science as living practice, not dead facts. This currency matters pedagogically. Students engage more when studying active questions rather than settled history. Knowing their learning connects to ongoing discovery motivates deeper engagement. Furthermore, the mathematical level is adjustable. Advanced students can dive into Einstein equations, quantum field theory, numerical relativity. Introductory students can focus on conceptual understanding, scaling arguments, qualitative reasoning. This flexibility makes Gravastars suitable across educational levels. High school physics can introduce basics. Undergraduate courses can explore details. Graduate seminars can grapple with cutting-edge research papers. Building educational pathways through topics, from simple to sophisticated, creates continuity. Students revisit concepts at increasing depth, building understanding progressively. Gravastars exemplify how frontier research can inform education at all levels. Not every topic does this. Some research is too technical, too specialized, too disconnected from foundations. But Gravastars connect fundamentals, gravity, quantum mechanics, light, matter, to extreme frontiers. They're pedagogically valuable precisely because they span this range. As the search continues, educational materials multiply. Researchers write review articles. Science communicators create visualizations. Documentary producers make films. These resources become educational tools. Teachers can assign review articles to advanced students. Show visualization videos in introductory courses. Use documentary clips to motivate discussions. The research naturally generates educational content. This symbiosis between research and education strengthens both. Research needs educated public support. Education benefits from authentic examples of science in action. Gravastars serve both purposes admirably. Looking forward, the next 2 decades will be decisive. LISA launches mid-2030s. Einstein Telescope and Cosmic Explorer hopefully become operational by 2040. Next-generation telescopes across electromagnetic spectrum come online. By 2045, we'll have vastly more data than today. Hundreds of gravitational wave detections, thousands of compact object observations, comprehensive sky surveys revealing every varying or moving object. This data deluge will enable definitive tests. Population statistics will have sufficient power to distinguish alternatives. Individual object measurements will achieve necessary precision. The ambiguity surrounding gravastars will resolve one way or another. Either they'll be confirmed, revolutionizing compact object astrophysics. Or they'll be ruled out, eliminating an attractive alternative and strengthening black hole paradigm. Or, perhaps most interestingly, observations will demand something even more exotic than current proposals. This third possibility deserves emphasis. Science repeatedly surprises us. Nature is not obligated to fit our categories. Reality often proves stranger than our imaginative speculations. We proposed gravastars to avoid singularities and preserve information. But maybe nature solves these problems differently. Maybe some hybrid structure exists, part black hole, part gravastar, part something we haven't conceived yet. Keeping minds open to unexpected possibilities is crucial. Dogmatic attachment to any particular model, even alternatives to mainstream, limits scientific progress. The history of astronomy is littered with confident predictions proven wrong. The steady-state universe, luminiferous ether, phlogiston, caloric fluid. Each seemed reasonable at the time. Each was abandoned when better alternatives emerged. Gravastars might join this list. Or black holes might. Or both concepts might require radical revision. We learn by proposing ideas and testing them rigorously. What we cannot do is stop asking questions. Cannot accept apparent mysteries as irreducible. Cannot declare certain topics beyond investigation. This leads to intellectual stagnation. The gravastar question remains open. It deserves continued investigation. Not blind faith in the hypothesis but genuine empirical inquiry. Follow evidence wherever it leads, even if destination surprises us. The instruments we're building, gravitational wave detectors, radio interferometers, X-ray telescopes, are agnostic about gravastars versus black holes. They simply observe nature with unprecedented precision. What they reveal will inform theory, not confirm preconceptions. This is proper scientific methodology. Build instruments capable of decisive measurements. Make observations carefully. Analyze data rigorously. Let nature speak. Listen to what she says. Sometimes nature whispers. Signals are faint, ambiguous, susceptible to multiple interpretations. Then patience is required. More data, better instruments, refined analysis. Sometimes nature shouts. Unexpected phenomena appear unmistakably, demanding explanations. Established theories prove inadequate. Paradigm shifts become necessary. We don't yet know which scenario applies to gravastars. The whisper or the shout. Gradual evidence accumulation or dramatic revelation. Both have precedent. Gravitational waves were whispers, predicted theoretically, sought for decades, finally detected after technological maturity enabled sufficient sensitivity. Dark energy was a shout, discovered unexpectedly from supernova observations, forcing cosmological revolution. Gravastars might follow either pattern. Or something between. Or something entirely different. The beauty of exploration is precisely this unpredictability. Certainty is for finished sciences, if such exist. Frontier research inhabits uncertainty. Discomfort with ambiguity is understandable but must be overcome. Ambiguity is the natural state when knowledge advances. The philosophical stance of accepting uncertainty while actively working to reduce it characterizes scientific thinking. It's neither blind skepticism rejecting all claims nor credulous acceptance believing everything. It's reasoned evaluation of evidence, proportional confidence to data quality, willingness to revise conclusions when new information arrives. Applied to gravastars, they're plausible given current understanding. Evidence is insufficient for confident acceptance. Continued investigation is warranted. Definitive conclusions await better data. This balanced position frustrates those seeking simple answers. Are gravastars real? Yes or no? We want definitive statements. Science often provides probabilities instead. Conditional statements. Nuanced positions. This nuance reflects reality's complexity. Simple binary answers rarely capture truth about sophisticated questions. The world doesn't organize itself for our cognitive convenience. Gravastars force confrontation with this complexity. They challenge us to think carefully about what we know, how we know it, what constitutes adequate evidence, how competing hypotheses should be evaluated. These metascientific questions are as important as object-level questions about compact object structure. How we think about evidence shapes what conclusions we reach. Methodology matters as much as data. Bad methodology can extract wrong conclusions from good data. Good methodology can extract maximal information from limited data. The quality of scientific reasoning determines knowledge quality. For gravastars, employing best methodology means several things. Rigorous statistical analysis quantifying confidence levels. Careful treatment of systematic errors. Conservative interpretation avoiding overstatement. Transparent reporting allowing others to verify results. These standards apply across science but are especially important for controversial claims. Extraordinary claims require extraordinary evidence, as the saying goes. Gravastars are sufficiently unusual that the evidentiary bar is high. This is appropriate, not unfair bias. Prior probability matters. Ideas inconsistent with vast amounts of established knowledge require stronger evidence than ideas fitting naturally into existing frameworks. Black holes fit naturally into general relativity. They're predicted directly from the theory, observed abundantly, explain numerous phenomena. Displacing them requires compelling reasons. Gravastars provide such reasons in principle, avoiding singularities, preserving information. But these conceptual advantages must be validated observationally. Elegant ideas failing empirical tests must be abandoned however beautiful their mathematics. Science is ultimately empirical. Theory guides, predicts, explains. But observation judges. When theory and observation conflict, theory must yield. This is what distinguishes science from other intellectual endeavors. Mathematics can pursue logical consistency independent of physical reality. Philosophy can explore concepts without empirical constraints. Science must always ground itself in observations of nature. For gravastars, we've reached the point where empirical grounding becomes critical. The theoretical case has been made. Predictions have been articulated. Now observations must decide. This is the exciting phase. Decades of theoretical preparation meet observational capability. The question moves from, could these exist, to, do these exist? The transition from possibility to actuality, or impossibility. Living through this transition, contributing to it however modestly, witnessing the resolution of long-standing uncertainty, this is the privilege and pleasure of contemporary researchers. Future generations will read about this period in history books. They'll see the trajectory clearly, with hindsight's perfect vision. The false starts and dead ends will seem obvious. The correct path will appear inevitable. But living it is different. We don't have hindsight. We navigate by imperfect maps in partially charted territory. Mistakes are inevitable. Backtracking is frequent. Progress is nonlinear. This messy reality contrasts sharply with clean historical narratives. History smooths over confusion, emphasizes successes, downplays failures. Textbook accounts make scientific progress seem logical, orderly, almost predetermined. The reality is far more chaotic. Ideas compete messily. Evidence is ambiguous. Researchers disagree vociferously. Consensus emerges slowly and incompletely. Even after major discoveries, residual debates persist. This chaos is not failure. It's how science actually works. Multiple perspectives attacking problems from different angles. Competition driving rigor. Disagreement forcing careful reasoning. If everyone agreed immediately, if every question had obvious answers, science would be easy. And unnecessary. The difficulty is the point. We're trying to understand things not immediately apparent, questions without obvious solutions. Gravastars exemplify this. If their existence were obvious, we'd have known for centuries. If their non-existence were obvious, the idea would never have gained traction. The fact that reasonable physicists disagree after 2 decades of discussion indicates genuine difficulty. This difficulty is intellectually engaging. Easy questions bore quickly. Hard questions sustain interest across careers. Gravastars provide the kind of sustained challenge that attracts talented researchers. Such challenges are rare. Most questions in physics have been answered. The remaining open problems tend to be either technically difficult, requiring better instruments, or conceptually radical, requiring new paradigms. Gravastars fall into both categories simultaneously. They're technically difficult to observe and conceptually radical in their implications. This makes them especially challenging and especially interesting. The technical difficulties drive instrument development. The conceptual challenges drive theoretical innovation. Both are necessary for scientific progress. Technology and theory advance together, each enabling the other. LIGO's detection of gravitational waves required both technological breakthroughs in detector sensitivity and theoretical advances in waveform prediction. Without precise theoretical templates, signals would be invisible in noise. Without sensitive detectors, even perfect templates would find nothing. Similarly for gravastars. We need both better detectors to see subtle differences from black holes and better theories predicting exactly what those differences are. Progress requires parallel advances. This synergy between theory and experiment is science at its best. Neither alone suffices. Together they're powerful beyond either separately. The infrastructure connecting theory to observation includes many components. Data pipelines processing raw detector output. Analysis algorithms extracting signals from noise. Simulation codes predicting theoretical expectations. Statistical frameworks comparing models to data. Each component requires expertise. No single person masters everything. Modern science is necessarily collaborative, bringing together diverse specialists. For gravitational wave astronomy, collaborations involve thousands of people. LIGO scientific collaboration includes over 1,300 members from 18 countries. Virgo collaboration adds hundreds more. These large collaborations represent fundamentally new ways of organizing scientific research. Traditional science was individuals or small groups. Einstein worked essentially alone on relativity. Even large experimental teams in early particle physics numbered dozens, not thousands. Modern big science requires coordinating enormous efforts. Managing these collaborations effectively is as challenging as the science itself. Ensuring equitable credit. Resolving disputes. Making collective decisions. Maintaining morale. These organizational challenges affect scientific productivity. Well-managed collaborations achieve more than poorly managed ones. Leadership quality matters. Governance structures matter. Culture matters. The sociology of science is not just peripheral concern. It directly impacts what science gets done, how quickly, how well. For Gravastar research specifically, the situation is intermediate. It's not yet large enough for massive collaborations but too complex for isolated individuals. Small teams of collaborators, loosely coordinated across institutions, characterize current work. This scale offers advantages. Communication is easier. Decision-making is faster. Individuals have more autonomy. Credit assignment is clearer. But also disadvantages. Resources are limited. Expertise gaps exist. Coordinating even small groups across institutions and countries presents challenges. As the field matures, organizational structures will evolve. If Gravastars become mainstream, larger collaborations will form. If they remain niche, small team structure will persist. Either way, human organization shapes scientific progress. The institutions we build, the communities we foster, the culture we cultivate, all influence what discoveries we make. Creating environments where diverse people work together effectively, where creativity is encouraged, where failures are tolerated, where rigor is maintained, this is as important as any technical advance. Science is human activity. Understanding it requires understanding human psychology, sociology, economics, politics. Pure focus on technical content misses crucial aspects of how knowledge actually develops. For Gravastars, the human story is rich. The researchers pursuing this question come from many backgrounds, many countries, many career stages. Some are established figures taking intellectual risks. Others are early career researchers betting careers on unconventional ideas. Their motivations vary. Some are driven by specific technical puzzles. Others by broader philosophical questions. Some by pure curiosity. Others by career calculation. This diversity of motivation is healthy. Science benefits from varied drivers. People pursuing questions for different reasons bring different strengths. The polymath motivated by wonder contributes differently than the specialist seeking incremental advance. Both are valuable. Both are necessary. A scientific ecosystem with only one type of researcher would be impoverished. Diversity creates resilience and richness. As we look toward future decades, maintaining this diversity becomes crucial. The pressures toward homogeneity are strong. Funding priorities channel research directions. Job markets favor certain specialties. Fashion influences which problems attract attention. Resisting these homogenizing forces requires deliberate effort. Valuing diverse research programs. Supporting unfashionable topics. Creating space for intellectual risk-taking. This is ultimately about scientific culture. What we value, what we reward, what we celebrate. Culture shapes individual choices which aggregate into collective outcomes. If we value only high-profile discoveries in mainstream topics, gravastars and similar alternatives languish. If we value careful investigation of well-posed questions regardless of fashion, such research thrives. Culture is not imposed from above. It emerges from countless individual choices. Every researcher's decisions about what to work on, what papers to cite, what talks to attend, these aggregate into cultural patterns. Changing culture requires collective action but begins with individual choice. Researchers can choose to engage seriously with alternative ideas even when unfashionable. They can cite papers exploring unconventional possibilities. They can attend talks on speculative topics. These small acts, multiplied across many individuals, reshape scientific culture. No single person determines culture but each contributes. For gravastars to receive fair hearing, the community must collectively decide that alternative hypotheses deserve serious investigation. This doesn't mean blind acceptance. It means proportional attention to ideas based on their conceptual merit and empirical promise. Currently, the community is reasonably balanced. Gravastars receive some attention, not dominant but non-trivial. Papers get published, grants sometimes fund, positions occasionally exist. This is neither full acceptance nor complete marginalization. It's appropriate given current evidence, plausible possibility worth investigating but not yet compelling enough to dominate. Maintaining this balance as more data arrives will be important. If evidence strengthens, attention should increase. If evidence weakens, attention should decrease. The response should track empirical support. This sounds obvious but is often violated. Ideas gain momentum for non-scientific reasons: charismatic advocates, institutional prestige, historical inertia. These factors can sustain ideas beyond their empirical shelf life. Similarly, good ideas can be prematurely rejected due to prejudice, misunderstanding, or social dynamics. Science is not purely objective, much as we aspire toward objectivity. Recognizing these human factors allows compensating for them. Building institutional safeguards against groupthink. Creating mechanisms for revisiting dismissed ideas. Maintaining archives preserving alternative viewpoints. These meta-scientific practices protect against common failure modes. They make the scientific enterprise more robust to biases and mistakes. The Gravistar question, whatever its ultimate resolution, demonstrates science working reasonably well. An alternative to mainstream theory was proposed. It wasn't immediately dismissed. It received some investigation. Predictions were articulated. Observational programs are underway. This is how it should work. Not perfect, never perfect. But functional. The system is processing the hypothesis, testing it, gathering evidence. Eventually conclusion will emerge from collective effort. The timescale may frustrate those seeking immediate answers. But good science is slow. Careful measurement takes time. Thoughtful analysis requires patience. Consensus builds gradually. Rushing to conclusions before evidence is adequate serves no one. Better to maintain uncertainty than embrace false certainty. The history of science is full of premature conclusions later overturned. Patience is a scientific virtue often undervalued. In a culture demanding rapid results, visible impacts, immediate applications, slow careful work seems wasteful. But fundamental science cannot be rushed. Nature reveals herself on her own schedule. We must adapt to her pace, not demand she adapt to ours. For gravastars, the pace is set by detector development, data accumulation, analysis refinement. These proceed as quickly as technology and human effort allow. We cannot force faster progress through wishful thinking. What we can do is maintain steady effort. Keep building better instruments. Keep analyzing data carefully. Keep refining theoretical predictions. Progress may be slow, but it's real. And suddenly, when sufficient data accumulates, clarity emerges. The phase transition from uncertainty to knowledge is often abrupt. Years of incremental progress reach critical mass and understanding crystallizes. This has happened repeatedly in scientific history. Continental drift was debated for decades, then suddenly accepted when seafloor spreading was discovered. Quarks were speculative, then suddenly real when deep inelastic scattering revealed substructure. Will gravastars follow this pattern? Will years of ambiguity suddenly resolve into clarity? Possibly. Or maybe the question stays forever ambiguous, with competing models perpetually fitting data equally well. Some questions may be intrinsically difficult to resolve decisively. If observational signatures are too subtle, if theoretical degeneracies are too severe, definitive answers may prove elusive. This would be frustrating but acceptable. Not every question must have clean answers. Sometimes reality is genuinely ambiguous from our observational vantage point. If this proves true for gravastars, future work might shift focus. Instead of definitively distinguishing gravistar from black hole, researchers might characterize the population of compact objects phenomenologically. What are their properties? How do they distribute? How do they evolve? These questions can be addressed even without knowing precise internal structure. Population statistics constrain formation mechanisms and evolutionary pathways even when individual object classification remains uncertain. This is practical approach when decisive individual measurements prove impossible. Focus on what can be measured reliably and extract maximum information from that. Such pragmatism is often necessary in astrophysics. We're studying objects at enormous distances, in extreme conditions, with limited observational access. Perfect information is unattainable. We work with what we can get. The art is extracting maximal insight from minimal data. This requires cleverness, creativity, sophisticated analysis. It's intellectually demanding even when observations are imperfect. Sometimes imperfect observations constrain theories more than perfect observations would. When forced to work indirectly, we develop general methods applicable broadly. Perfect observations might give specific answers without generalizable insights. This is silver lining to observational limitations. Necessity drives methodological innovation. Constraints inspire creativity. For gravastars, current observational limitations are driving novel analysis techniques, sophisticated modeling, creative predictions. Even if gravastars prove unobservable with current technology, these advances benefit broader fields. The search for gravastars has already improved gravitational wave analysis methods, refined compact object models, advanced understanding of extreme matter states. These are valuable outcomes independent of gravastar existence. This is how science actually provides value. Not just through successful confirmations but through productive explorations. Even unsuccessful searches teach us, develop capabilities. Train researchers, advance techniques. Judging science solely by successful confirmations misunderstands the process. Most hypotheses prove wrong. Most experiments yield no results. Most projects fail to achieve original goals. This isn't failure. It's exploration. We learn what doesn't work, what isn't there, what needs revision. Negative results are results. They constrain possibilities, guide future efforts, prevent wasted time on dead ends. For gravastars, even definitive disproof would be valuable knowledge. It would tell us something about how nature behaves at extremes. It would strengthen our understanding of why black holes form as they do. It would clarify limits of exotic matter configurations. So the investigation is valuable regardless of outcome. This is crucial for sustaining research through uncertain periods. The journey matters, not just destination. This philosophical stance toward research helps maintain motivation when progress is slow or results are ambiguous. Focus on process quality, not outcome certainty. Do good work, ask good questions, use good methods. Results will follow eventually, whatever they are. For individuals pursuing gravastar research, this perspective is psychologically healthy. Basing self-worth on confirming hypotheses is recipe for disappointment. Most hypotheses fail. If personal success requires specific outcomes, frustration is inevitable. Better to define success as asking interesting questions and investigating them rigorously. By that standard, gravastar research is already successful. Interesting questions have been posed. Rigorous investigation is ongoing. Outcomes remain uncertain but the work is valuable. This healthier relationship to scientific uncertainty benefits individuals and fields. It reduces pressure to overstate results, to see patterns in noise, to claim premature success. It allows honest acknowledgement of uncertainty without shame. Science advances faster when uncertainty is embraced rather than feared. When researchers feel safe saying, "We don't know yet," instead of forcing premature conclusions. When ambiguity is recognized as normal state of frontier research. Creating cultural space for this honesty requires collective effort. Senior researchers must model it. Journals must publish null results. Funders must reward careful negative results as much as flashy positive ones. These cultural changes happen slowly but matter enormously. They shape what kind of science gets done and how. The technical architecture of gravitational wave detectors reveals engineering at its most sublime. Consider LIGO's laser system. A 200-watt infrared laser beam enters the interferometer. Through power recycling mirrors, this amplifies to 100 kilowatts circulating in the arms. That's enough power to vaporize any imperfection in the optics within microseconds. The mirrors themselves are masterpieces of precision. Fused silica cylinders weighing 40 kilograms, polished to atomic scale smoothness. Surface irregularities cannot exceed 1 atom's height across the entire 34 centimeter diameter. Any larger imperfections would scatter light, introducing noise that drowns out gravitational wave signals. Suspending these mirrors presents its own challenge. They must hang freely, isolated from ground vibrations, yet remain precisely positioned. The suspension system uses 4 stages of pendulums, each stage filtering vibrations from the stage above. The final mirror hangs on fused silica fibers thinner than human hair yet strong enough to support 40 kilograms. At room temperature, thermal noise from molecular motion would jiggle the mirrors too violently. Advanced LIGO operates at room temperature by necessity. Cooling 40 kilogram optics is impractical. Instead, careful design minimizes thermal noise's impact. The mirror material, suspension fibers, coating composition, all chosen to minimize thermally induced motion at frequencies where gravitational waves exist. Even so, thermal noise remains a limiting factor. Future detectors like the Einstein telescope will operate at cryogenic temperatures. Cooling mirrors to 10 Kelvin reduces thermal noise dramatically. But this introduces new challenges. Cooling systems add complexity. Different materials are needed. Fused silica's thermal properties degrade at cryogenic temperatures. Silicon becomes the preferred material, requiring entirely new mirror fabrication techniques. These technical choices cascade through detector design. Every component must be optimized simultaneously. Change one thing, and 10 others must adapt. The system is tightly coupled, requiring holistic design approach. Designing LIGO took decades. Thousands of technical decisions, each backed by careful analysis and often experimental testing. Should mirrors be sapphire or fused silica? Should suspensions use steel wire or silica fiber? Should vacuum chambers be stainless steel or aluminum? Each choice affects performance, cost, schedule. Optimizing simultaneously is mathematically intractable. Engineers rely on experience, intuition, iterative refinement. They build prototypes, test them, learn from failures, iterate. This process cannot be rushed. Cutting corners produces inferior detectors that cannot achieve science goals. The only path is patient, careful engineering, accepting that some attempts will fail, that unexpected problems will emerge, that solutions will require creativity and persistence. LIGO's development illustrates this. Initial LIGO, operational from 2002 to 2010, never detected gravitational waves. Sensitivity fell short of requirements. This wasn't failure, it was planned. Initial LIGO was always intended as stepping stone to advanced LIGO. The decade of null results provided invaluable operating experience. Engineers learned which components underperformed, which noise sources were problematic, where improvements would be most impactful. Advanced LIGO incorporated these lessons. Redesigned seismic isolation, higher laser power, better mirror coatings, improved electronics. The cumulative effect was tenfold sensitivity improvement. And with that improvement came success. Within days of advanced LIGO beginning operations in September 2015, it detected GW150914. The first gravitational wave observation. Binary black hole merger. One of the most important scientific discoveries of the 21st century. This success validated decades of investment. Vindicated researchers who persisted through years of null results. Demonstrated that patience and persistence pay off in science. For gravastars, the lesson is patience. Current detectors are just reaching adequate sensitivity. In another decade, with next-generation instruments, observational capability will be vastly superior. If gravastars exist and produce distinguishable signatures, future detectors will find them. The electromagnetic spectrum offers complementary views. X-ray telescopes like Chandra and XMM Newton have observed thousands of compact object systems. Their spectra encode information about accretion physics, spin, mass, magnetic fields. Spectroscopy is astrophysics's most powerful tool. Light carries information. By analyzing which wavelengths are present, absorbed, or emitted, we infer conditions at the source. Temperature, density, composition, velocity, magnetic field strength, all encoded in spectral features. For compact objects, iron K-alpha line is particularly diagnostic. Iron atoms in the accretion disk are irradiated by high-energy photons from near the compact object. This ionizes iron, and when electrons recombine, they emit characteristic X-rays at 6.4 keV. But these X-rays don't emerge unchanged. Gravity redshifts them. Doppler shifts from orbital motion broaden the line. General relativistic effects warp the line profile into distinctive shapes. By modeling these effects, astronomers infer the inner disk's properties. How close does matter orbit before plunging in? Does it plunge at all or hit a surface? These questions have different answers for black holes versus gravastars. Distinguishing these scenarios requires high spectral resolution. Current instruments struggle. The iron line extends across several keV energy range. Disentangling redshift from Doppler from relativistic effects needs finer energy resolution than available. Next-generation instruments promise improvement. Athena, planned for 2030's launch. We'll have calorimeter detectors with unprecedented energy resolution. It can measure X-ray energies to within a few electron volts, 100 times better than current instruments. With this capability, the detailed iron line shape becomes accessible. Subtle differences between black hole and gravastar predictions become measurable. Not in single observations, signal-to-noise remains limiting, but in averages over multiple long observations. This is the trend across astronomy. Individual measurements are noisy. But averaging over many measurements with well-understood systematics yields precise constraints. Statistical power comes from multiplicity, not perfection of individual data points. For gravastars, this means the answer emerges from population studies. Dozens or hundreds of compact object systems observed carefully. Their collective properties compared with theoretical predictions. Bayesian model comparison determining which scenario best fits the ensemble. This is less dramatic than a single smoking gun observation definitively proving gravastar existence. But it's more realistic. Most astrophysical conclusions emerge from accumulated evidence, not isolated crucial experiments. The accretion process itself offers clues. When matter spirals toward a compact object, it heats up through friction. Temperature increases inward as orbital velocity grows. The innermost stable orbit, where matter moves fastest before plunging in, produces the hottest, hardest X-rays. For black holes, this innermost orbit's radius depends on spin but not on horizon presence. Even though matter disappears through the horizon, it doesn't hit anything. There's no collision, no sudden conversion to radiation. Matter simply crosses the point of no return and continues falling inward invisibly. For gravastars, matter collides with the surface. This collision converts kinetic energy to radiation abruptly. The temperature and spectrum of this boundary layer radiation should differ from standard accretion disk models assuming horizons. Computing expected spectra requires sophisticated radiative transfer calculations. Matter near the surface exists in extreme conditions, relativistic velocities, intense radiation fields, strong magnetic fields. Modeling all these effects simultaneously challenges computational capabilities. Current calculations make simplifying assumptions. They're guides, not precise predictions. But they indicate the kinds of spectral differences we should look for. Harder spectra, different variability timescales, unusual reflection features. Observers search for these signatures in existing data. So far, nothing convincing. But the data quality is marginal. Confident conclusions require better observations. The radio regime provides yet another window. Very long baseline interferometry achieves angular resolution finer than any other technique. By combining radio telescopes across continents, astronomers synthesize aperture sizes equal to Earth's diameter. At millimeter wavelengths, this gives angular resolution around 20 microarcseconds. That's small enough to resolve structure near supermassive compact objects in nearby galaxies. M87 and Sagittarius A have been imaged this way. These images show the shadow, a dark central region surrounded by bright emission from the accretion disk and jet. The shadow's size and shape depend on the compact object's properties. For a black hole, the shadow is roughly 2.6 times the Schwarzschild radius. This is the photon sphere radius, where light orbits the black hole. Photons approaching closer spiral inward. From outside, this creates dark region. For a gravastar, the situation differs subtly. The photon sphere still exists, but photons don't disappear at the surface. They can reflect, though enormously redshifted. This might create faint emission inside the shadow, distinguishable with sufficient sensitivity. Current EHT images don't have adequate dynamic range to detect this. The bright ring around the shadow overwhelms any faint internal emission. But future improvements, more telescopes, better receivers, space-based baselines, could enable detection. If faint emission exists inside the shadow, it would indicate a reflecting surface rather than a horizon. Not definitive proof of gravastars, other exotic objects might also reflect, but strong evidence against standard black holes. This is how science progresses in practice. Not through single definitive tests but through multiple lines of evidence converging. Gravitational waves provide one constraint. X-ray spectroscopy another. Radio imaging a third. Collectively, they narrow possibilities. When all evidence points consistently toward one conclusion, confidence grows. When evidence conflicts, more investigation is needed. The gravastar question currently sits in this ambiguous zone. Some hints suggestive, nothing definitive, plenty of room for continued debate. Computational astrophysics has revolutionized our ability to model extreme environments. Simulating neutron star mergers or accretion onto compact objects requires solving Einstein's equations coupled with hydrodynamics, magnetic fields, neutrino transport, nuclear physics. No analytic solutions exist for such complexity. Numerical simulation is essential. But the computational cost is staggering. A single merger simulation can consume millions of CPU hours on supercomputers. The equations are stiff, small time steps required for numerical stability. The spatial resolution must be fine enough to capture relevant physics but coarse enough to be computationally feasible. The computational domain must be large enough to avoid boundary effects but small enough to be affordable. Balancing these competing requirements demands expertise and experience. Computational astrophysicists spend careers developing codes, testing them on idealized problems, gradually increasing realism. For gravastars, simulations are essential for predicting observational signatures. How does a gravastar merger differ from black hole merger? What gravitational waveforms do they produce? How does the remnant oscillate? These questions cannot be answered analytically. The system is too complex. Only numerical simulation can provide quantitative predictions. But simulations require knowing the equation of state, the relationship between pressure and density, for gravastar matter. This isn't well known. It depends on quantum gravity physics we don't fully understand. Simulators must make assumptions. Try different equations of state, see how results change. This gives sense of which predictions are robust and which depend sensitively on uncertain physics. Results show that gravastar mergers can produce gravitational waves similar to black hole mergers, with subtle differences in late-time ring-down. The differences are small, requiring excellent detector sensitivity to detect. This is encouraging and discouraging simultaneously. Encouraging because it means gravastars are potentially observable. Discouraging because it means distinguishing them is very difficult. The simulation results guide observers. They know what to look for, what analysis techniques might extract weak signals. Without simulation guidance, observers would be searching blindly. This synergy between simulation and observation exemplifies modern astrophysics. Theorists use simulations to predict observables. Observers search for those predictions. When observation and prediction match, confidence in theory increases. When they disagree, theory must adapt. For gravastars, we're still early in this cycle. Simulations are developing. Observations are accumulating. Predictions and data are being compared. No definitive conclusions yet, but the process is functioning. Machine learning increasingly plays a role in this analysis. Neural networks can be trained to recognize gravastar signals in noisy data. They learn patterns human analysts might miss. Training requires simulated data. Researchers generate thousands of artificial gravitational wave signals, some from black hole mergers, some from gravastar mergers. Neural networks learn to distinguish them. Then networks are applied to real data. They flag candidate gravastar events for detailed human analysis. This focuses human attention on the most promising candidates. Machine learning is not magic. Networks can be fooled by noise patterns resembling signals. They can miss genuine signals if they're sufficiently unusual. They require careful validation and skeptical evaluation. But they're powerful tools. They enable searching larger parameter spaces than humans could manually explore. They find subtle patterns invisible to simple analysis techniques. For gravastars, machine learning might prove decisive. If the signatures are subtle but present, properly trained networks might extract them from data. If signatures are absent or indistinguishable from noise, networks will reveal that too. Either outcome advances knowledge. Finding signals confirms gravastars. Null results after exhaustive AI-assisted search would strongly constrain their existence or abundance. The international nature of modern astronomy deserves emphasis. Gravitational wave detectors exist on multiple continents. Observatories span the globe. Researchers collaborate across borders, cultures, languages. This internationalism is necessity, not choice. Earth-scale instruments require global participation. No single nation can build the necessary infrastructure alone. But it's also opportunity. Different perspectives enrich research. Cultural diversity enhances creativity. International collaboration builds relationships transcending politics. Science as bridge between nations, fostering cooperation, creating shared goals. This idealistic vision often manifests in major projects. The Large Hadron Collider, International Space Station, Event Horizon Telescope, all exemplify international scientific cooperation. Gravitational wave astronomy continues this tradition. LIGO is American but with international partners. Virgo is European. CAGRA is Japanese. Future detectors in India and Australia will further expand the network. This global network provides scientific advantages beyond political symbolism. More detectors mean better sky coverage. Simultaneous detection at multiple sites enables source localization. Different detector orientations and noise characteristics enable cross-validation. For gravastars, the International Detector Network is essential. Definitive detection will require multiple confirmations at multiple sites. No single detector observation will convince the skeptical community. But consistent signals across independent instruments become compelling. This need for reproducibility is fundamental to science. Extraordinary claims require extraordinary evidence, and extraordinary evidence means independent confirmation. The social organization enabling this international collaboration is fascinating. How do thousands of researchers across dozens of institutions coordinate? How are decisions made? How is credit allocated? Large collaborations develop governance structures. Committees oversee different aspects. Working groups tackle specific problems. Publications are authored collectively, with hundreds or thousands of names. This collective authorship frustrates those accustomed to traditional science where credit goes to specific individuals. Who gets recognition when a paper has 1,000 authors? How do we evaluate contributions? These are genuine challenges without perfect solutions. Collaborations develop internal systems tracking contributions. But external evaluators struggle.